At the center of our galaxy, there is something waiting, something with the mass of 4 million suns compressed into a region smaller than the orbit of Mercury. Something so dense that if you could somehow approach it, the laws of physics as you've known them your entire life would begin to unravel in front of you. Its name is Sagittarius A star. It sits 26,000 light-years from the chair you are sitting in right now. And it is a black hole, not a distant curiosity in some far-off galaxy, not a theoretical prediction scribbled on a chalkboard. The monster black hole at the heart of the Milky Way, our black hole. For decades, astronomers tracked stars whipping around an invisible point in space at speeds that should not be possible. Speeds that could only mean one thing: something massive, something dark, something with gravity so extreme that not even light can escape it, was hiding in plain sight at the galactic core, and the evidence kept piling up until there was no other explanation left. But here is the part no one tells you. Black holes are not eternal. Stephen Hawking proved it. They evaporate, they leak, and over timescales so vast they make the age of the universe look like a heartbeat. They vanish. So what are we actually looking at when we point our telescopes at Sagittarius A star? What would you see? What would you feel if you could fall past the point of no return? And how did objects this violent, this incomprehensible, end up shaping every galaxy in the observable universe? This is not a story about destruction. It is a story about the most extreme physics in nature, the boundaries of space-time itself, and what happens when you follow the math all the way down into the dark. This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Stars do not die quietly. When a star massive enough reaches the end of its life, the universe doesn't give it a retirement party. There's no slow fade, no gentle dimming into the dark. What happens instead is violence on a scale that makes every human war, every natural disaster, every bomb we've ever detonated look like a child's sneeze. The star collapses, then it explodes. And what's left behind, if the star was heavy enough, is something so strange that for most of human history we didn't have the physics to even imagine it. We're going to talk about how black holes are born. Not the supermassive monsters sitting at the centers of galaxies. We'll get to those later, but the smaller ones, the stellar mass black holes. The kind that form when a single star, one object, gives up the fight against gravity and folds in on itself until it punches a hole in the fabric of space itself. To understand that process, you need to understand what a star actually is, and the answer is simpler than you'd think. A star is a bomb that refuses to go off. It's a massive ball of hydrogen held together by its own gravity, crushing itself inward with such force that the core gets hot enough to fuse hydrogen atoms into helium. That fusion releases energy, a lot of energy, enough to push outward against the crushing weight of all that mass trying to collapse inward. For millions or billions of years, those two forces, gravity pulling in, fusion pushing out, sit in perfect balance. The star holds. It shines, it looks stable. It is not stable, it is a war in slow motion. Our sun has been fighting that war for about 4.5 billion years. It will keep fighting for another 5 billion or so before it runs out of hydrogen in its core and the balance tips. But our sun is small. When it finally loses, it won't have enough mass to collapse all the way down into a black hole. It'll puff up into a red giant, shed its outer layers into space, and leave behind a dense, hot core called a white dwarf. A smoldering ember the size of Earth, but with the mass of a star. That's the fate of most stars in the galaxy. Quiet deaths, slow deaths. Deaths that end in cooling and fading rather than catastrophe. But if a star is born with more than about 8 times the mass of our Sun, the ending is different, much different. Massive stars burn hotter and faster than their smaller cousins. They rip through their hydrogen fuel in just a few million years instead of billions. When the hydrogen in the core runs out, the core contracts, the temperature spikes. And if the star is big enough, it starts fusing helium into carbon, then carbon into oxygen, then oxygen into neon, neon into magnesium, magnesium into silicon. Each stage burns faster than the last. Hydrogen fusion can last millions of years. Silicon fusion lasts about a day. At each step, the star is buying time, building heavier elements in its core, releasing energy, holding off the collapse. But there's a limit. There's always a limit. And the limit is iron. Iron is where fusion stops paying dividends. Fusing lighter elements into heavier ones releases energy. That's what powers the star. But once you reach iron, the process flips. Fusing iron into anything heavier costs energy instead of releasing it. The core of a massive star, after burning through every other fuel it has, ends up as a ball of iron ash. No more fusion. No more outward pressure. Just gravity, pulling inward with nothing left to fight it. What happens next happens fast. The core collapses, not over millions of years, not over days. In about 1 second, a core the size of Earth, weighing more than our entire Sun, implodes down to a sphere roughly 20 kilometers across. 20 kilometers. The density becomes so extreme that protons and electrons are crushed together into neutrons. The stuff that made up atoms, the empty space between the nucleus and the electron cloud, all of that gets erased. What you're left with is neutron degenerate matter. A single atomic nucleus the size of a city. This is a neutron star, one of the densest objects in the universe. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. If you could somehow scoop some up and drop it, it would punch straight through the planet and keep going. For some collapsing stars, this is where the story ends. The core hits neutron degeneracy, and that's stable enough to hold. The outer layers of the star, which were still falling inward when the core suddenly stopped, slam into that neutron core and bounce. The rebound sends a shock wave racing back outward through the star's outer envelope, ripping it apart. The star explodes. We call that explosion a Type II supernova, and for a few weeks it can shine as brightly as an entire galaxy. Everything outside the core, all the hydrogen, helium, carbon, oxygen, every element the star spent its life building, gets blasted into space at a significant fraction of the speed of light. That ejected material will drift through the galaxy, mix with clouds of gas and dust, and eventually seed the next generation of stars and planets. Every atom of carbon in your body, every atom of oxygen you breathe, was forged inside a star and scattered by a supernova. You are made of exploded stars. That's not poetry, that's astronomy. But if the core is too massive, even neutron degeneracy can't hold it. There's a limit to how much mass a neutron star can support, somewhere around 2 to 3 times the mass of our Sun. If the collapsing core is heavier than that, nothing in known physics can stop the collapse. The neutrons themselves get crushed. The core keeps falling inward. Density goes infinite. Space-time curves so sharply that it folds in on itself, and you get a black hole. Not a big black hole. Not yet. A stellar mass black hole. Something with maybe 3 times the mass of our Sun, maybe 10, maybe 20, depending on how massive the original star was and how much mass got blown away in the supernova. These objects are small. The event horizon, the boundary beyond which nothing can escape, might be only a few dozen kilometers across. You could fit one inside a large city, but the mass contained in that space is staggering. And the gravity is absolute. This is where things stop making intuitive sense. A neutron star, as extreme as it is still an object. It has a surface. You could, in theory, if you had a spacecraft made of something absurdly strong and heat-resistant, land on a neutron star. You'd be crushed and irradiated instantly, but the surface is there. A black hole has no surface. Once the collapsing core crosses a certain threshold, it doesn't stop at some incredibly dense but still physical object. It keeps collapsing, past any scale we have words for. The matter that made up the core, all those neutrons, all that mass, falls into a point of infinite density that physicists call a singularity. Whether singularities actually exist, or whether something else happens at that scale, is an open question. General relativity says they exist. Quantum mechanics says that's probably nonsense. Nobody knows. What we do know is that once the core collapses past the event horizon, it's gone, not hidden, not compressed into something we can't see, gone from the universe in any meaningful sense. The only things left behind are mass, spin, and if the star was charged, electric charge. Everything else, every detail about what the star was made of, how it was structured, what it looked like, erased. A black hole is the ultimate amnesia. It remembers almost nothing about what fell into it. And that event horizon, that boundary, is where physics gets genuinely strange. It's not a physical barrier. There's no wall, no shell, no surface. If you were falling toward a black hole, you wouldn't feel anything special as you crossed the event horizon. Locally, space would seem normal. You could look at your watch, it would tick normally. You could shine a flashlight. The light would behave as expected. But from the perspective of someone watching from far away, you would appear to slow down as you approached the horizon. Your image would redshift, dimming and stretching, and you would never quite seem to cross. Time dilation near the event horizon is so extreme that to an outside observer, you'd be frozen at the edge forever. To you, you'd cross in finite time and then, very quickly, stop existing in a process called solvitization, where tidal forces stretch you into a thin stream of atoms. Neither perspective is wrong. They're both correct descriptions of the same event from different reference frames. That's relativity for you. Stellar mass black holes are not rare. Our galaxy alone probably contains tens of millions of them. Most formed billions of years ago, when the Milky Way was younger and star formation was more violent. They drift through the galaxy now, invisible, detectable only when they happen to pass near another object and their gravity gives them away. Some are in binary systems, orbiting a companion star and slowly pulling gas off its surface. That gas spirals inward, heats up to millions of degrees, and emits X-rays before disappearing across the event horizon. Those X-ray binaries are how we've detected many of the stellar mass black holes we know about. The black hole itself is invisible. The stolen gas, glowing as it dies, is not. One of the closest known black holes to Earth is about 1,500 light-years away in the constellation Telescopium. It was discovered in 2020, not by X-rays, but by the way its gravity made a nearby star wobble. The star is in orbit around something we can't see, something massive. The orbital mechanics point to an object roughly 10 times the mass of the Sun packed into a space small enough that it can't be anything but a black hole. There are probably closer ones. Statistically, there should be. But black holes that aren't actively feeding are nearly impossible to find. They just sit there, waiting, bending space around them, contributing nothing to the sky except a faint gravitational tug that we can only detect if we happen to be looking in exactly the right place, with exactly the right instruments. The process that makes a stellar mass black hole, core collapse followed by a supernova, is well understood now. We've built computer simulations that can model the collapse in extraordinary detail. We've observed supernovae in other galaxies and measured their light curves, their spectra, the elements they scatter. The picture is consistent. When a massive star dies, if the core is heavy enough, you get a black hole. Simple, brutal, efficient. But here's the part that should bother you. Nobody has ever watched a stellar mass black hole form. We've seen the explosions, we've detected the remnants, we've mapped the X-ray binaries and measured the wobbles in distant stars. But the actual moment when a collapsing core crosses the event horizon and becomes a black hole? That happens in less than a second, deep inside a dying star, hidden behind layers of infalling gas and blinding light from the supernova. By the time we see the explosion, the black hole has already been sitting there for hours. It's like watching a magician's trick in reverse. You see the reveal, the doves flying out of the hat, the audience clapping, but you missed the sleight of hand. The moment the trick actually happened, the instant the core collapsed and space broke, that moment is hidden, and it will probably stay hidden, because the conditions inside a collapsing stellar core are so extreme, so violent, that no signal from the interior can reach us before the event horizon forms and seals it off. We know it happens, the math is clear, the observations line up, massive stars explode. Some leave behind neutron stars, some leave behind black holes. The dividing line is mass. If the core is too heavy for neutron degeneracy to hold, collapse continues. That's not speculation. That's just gravity doing what gravity does when nothing is strong enough to stop it. Stellar mass black holes are in a sense the simplest kind. They form from single objects. One star dies, one black hole appears. The process is violent, but it's local. The black hole that forms weighs a few times more than our Sun, maybe 10, maybe 20 at the absolute upper end. It's dangerous if you get close, but on a galactic scale, it's a footnote, a dead star, a cosmic grave marker. But stellar mass black holes are not the only kind, and they are not the ones that define galaxies, shape the structure of the universe, or sit at the center of nearly every large galaxy we've ever observed. Those black holes, the ones that weigh millions or billions of times the mass of our Sun, don't form from the collapse of a single star. They can't. No star is massive enough to leave behind a billion solar mass black hole when it dies. Those monsters were built by a different process, a slower one. A process that has been running since the universe was young. And the strangest part, we have one of those monsters in our own galaxy, right now, sitting 26,000 light-years away in the direction of the constellation Sagittarius, 4 million times the mass of our Sun, confined to a region smaller than our solar system. It doesn't glow. It doesn't scream. It just sits there, quietly holding the Milky Way together, a permanent scar in space-time that we only confirmed existed a few decades ago. If you want to understand what a black hole actually is, not in theory, not in math, but as a real object that we can point to and measure, you have to understand what we found at the center of our galaxy. Because that discovery didn't just confirm that supermassive black holes exist. It forced us to accept that we've been living in orbit around one for our entire history as a species, and we never noticed. We've talked about how black holes are born. Now we need to talk about what they actually are, because the popular image, the one you've probably been carrying around in your head since you first heard the term, is almost certainly wrong. Black holes are not holes. They don't suck things in like cosmic vacuum cleaners. They don't reach across space and grab passing spaceships. If you swapped our sun out for a black hole of exactly the same mass right now, Earth's orbit wouldn't change. We'd freeze to death in the dark, yes, but gravitationally, nothing would move. The planets would keep their lanes. The math wouldn't care that the sun had been replaced with something infinitely denser and considerably more disturbing. A black hole is not a tunnel to another dimension. It's not a gateway, not a wormhole, not a shortcut to the other side of the universe. It is, in the most literal sense possible, a region of space where gravity has become so strong that nothing, not even light, can escape once it crosses a particular boundary. That boundary has a name. We call it the event horizon, and it is the single most unforgiving border in the known universe. To understand why that boundary exists, you have to understand what gravity actually is. And that requires going back to 1915 to a set of equations published by a German physicist named Albert Einstein, equations that rewrote the rules. Before Einstein, gravity was a force. Isaac Newton described it that way in the late 1600s, and his description worked beautifully for more than 2 centuries. Gravity, in Newton's model, was an invisible pull between any 2 objects with mass. The more massive the objects, the stronger the pull. The farther apart they were, the weaker it got. Simple, predictable, useful enough to send rockets to the moon. But Newton's gravity had a problem. It didn't explain how the force was transmitted. If the sun suddenly vanished, Newton's equations said Earth would fly off into space immediately. But how would Earth know the sun was gone? How does gravity propagate across 150 million kilometers of empty space instantaneously? Newton himself admitted he had no answer. He famously wrote that he would not feign hypotheses about the mechanism. The math worked. That was enough. Einstein's answer was deeper and stranger. Gravity, he said, isn't a force at all. It's geometry. Mass curves space-time. Picture space-time as a stretched rubber sheet. Now place a heavy ball in the center. The sheet bends. The heavier the ball, the deeper the curve. If you roll a smaller ball across the sheet, it doesn't travel in a straight line anymore. It curves toward the heavy ball, not because the heavy ball is pulling it, but because the sheet itself is curved. The small ball is following the straightest possible path through curved space. Physicists call that path a geodesic. We call it an orbit. This is general relativity. And it doesn't just describe gravity differently. It describes a universe where space and time are woven together into a single fabric, where mass and energy warp that fabric, and where what we experience as gravity is just objects moving along the curves. Light itself follows those curves. Bend space sharply enough, and light has to curve with it. Bend it even more, and light can't climb back out. That's a black hole. Not an object in space, but a region where space itself has been bent past the point of repair. Einstein's equations allow for this. In fact, they practically demand it. Within months of Einstein publishing General Relativity, a German physicist named Karl Schwarzschild, serving on the Russian front during World War I, worked out an exact solution to Einstein's field equations. Schwarzschild was looking at the simplest possible case, a non-rotating, uncharged spherical mass, and his solution described the curvature of space-time around it. What he found was that if you compressed enough mass into a small enough space, the equations predicted something bizarre. A radius where the curvature became so extreme that the escape velocity exceeded the speed of light. That radius is now called the Schwarzschild radius. For our Sun, it's about 3 kilometers, meaning if you could somehow crush the entire Sun down into a sphere 6 kilometers across, it would become a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. Crush our entire planet into a sphere the size of a marble, and it would disappear behind an event horizon. The mass doesn't change. The gravity at a distance doesn't change. What changes is the density. Pack enough mass into a small enough volume, and space-time curves so sharply that nothing inside a certain boundary can ever leave. That boundary is the event horizon. It's not a physical surface. There's no shell, no membrane, no wall. If you were falling toward a black hole and you crossed the event horizon, you wouldn't feel a thing. Locally, space would seem perfectly normal. You could look at your hands, they'd look the same. You could check your watch, it would tick forward just like it always had. You wouldn't notice the moment you crossed. But from the perspective of someone watching you from far away, something very different would happen. As you approached the event horizon, they would see you slow down. Your movements would become sluggish. The light reflecting off your body would redshift, stretching toward the red end of the spectrum as the photons struggled to climb out of the deepening gravitational well. You would dim, you would freeze, and you would never quite seem to cross. To an outside observer, you'd be stuck at the edge of the black hole forever, your image fading and redshifting into invisibility, but never actually disappearing. To you, you'd cross in finite time. You'd fall past the event horizon, and then, depending on the size of the black hole, you'd have anywhere from a fraction of a second to a few hours before you hit the singularity. Both perspectives are correct. That's relativity. Time is not absolute. It flows at different rates, depending on how deep you are in a gravitational field. Near a black hole, that difference becomes extreme. This is not theory, this is math. The equations are clear, and every test we've run, every observation we've made, has confirmed that general relativity describes gravity with absurd precision. When we send spacecraft to other planets, we use Einstein's equations, not Newton's, because Newton's aren't accurate enough. When we synchronize the clocks on GPS satellites, we have to account for the fact that time runs slightly faster in orbit than it does on the ground. If we didn't correct for that, GPS would drift off by kilometers within a day. Relativity is not speculative, it's engineering. And relativity says that black holes exist, not as a curiosity, not as a mathematical artifact, but as real objects that form whenever you concentrate enough mass in a small enough space. Now here's where things get uncomfortable. What happens at the very center? In Einstein's equations, the curvature at the center of a black hole becomes infinite. All the mass that collapsed to form the black hole, all the matter that has fallen in since, gets compressed into a point of zero volume and infinite density. Physicists call that a singularity. It's a place where the equations break down, where the numbers stop making sense. Divide by zero and the math explodes. Do singularities actually exist? Nobody knows. General relativity says they do, but general relativity doesn't play well with quantum mechanics, and at the scales we're talking about, quantum effects should matter. Some physicists think the singularity is a sign that general relativity is incomplete, that there's some deeper theory, some combination of relativity and quantum mechanics that would smooth out the singularity into something less absurd. String theory tries to do that. Loop quantum gravity tries to do that. Nobody has succeeded yet. What we do know is that whatever is happening at the center, it's sealed off from the rest of the universe by the event horizon. Information can't escape, light can't escape. The singularity, real or not, is hidden. And that's probably a good thing, because if you could see a naked singularity, a place where the laws of physics genuinely break, the universe would have a problem. Physicists call this the cosmic censorship hypothesis. The idea that nature abhors naked singularities and always wraps them in event horizons. So far, every black hole we've observed seems to follow that rule. Let's talk about what happens if you get close, not to the singularity. You're not getting anywhere near that and remaining intact. Let's talk about what happens if you approach the event horizon of a stellar mass black hole, the kind we talked about in the last chapter. Tidal forces will kill you. Quickly, gravity gets weaker with distance. That's true for any mass, but near a black hole, the gradient becomes steep, very steep. If you were falling feet first toward a black hole, your feet, being closer to the center, would experience stronger gravity than your head. The difference in pull between your feet and your head would stretch you, lengthen you. At the same time, gravity would compress you from the sides, squeezing you inward. This process has a name. Scientists call it spaghettification, because you would be stretched into a long, thin noodle before being torn apart at the atomic level. How close you'd have to get before this happened depends on the size of the black hole. For a stellar mass black hole, say 10 times the mass of the Sun, you'd start feeling uncomfortable tidal forces well outside the event horizon. You'd be ripped apart long before you crossed. For a supermassive black hole, one with millions or billions of solar masses, the event horizon is much, much larger, and because the gradient of gravity is gentler at that scale, you could actually cross the event horizon intact. You'd still die, you'd still hit the singularity. But you'd have a little time to look around first. Not that there'd be much to see, just darkness. And the slowly dimming stars behind you, their light stretched and distorted by the curvature of space. There's something deeply unsettling about the event horizon. It's a one-way membrane. Cross it in one direction and you can never go back. There's no force holding you in. You're not being pulled. You're just moving through space, following a geodesic, the straightest possible path. But every geodesic that crosses the event horizon leads inward. All of them. There is no outward. Outward stops being a direction you can point to. The geometry of space-time itself has bent so sharply that every future direction is toward the center. Think about that for a second. We're used to thinking about space as something neutral, a stage where things happen. But near a black hole, space is not neutral. It's tilted, it's falling, and once you're inside the event horizon, you're falling with it. Not toward the black hole, you are inside the black hole. The singularity is not a place you're traveling to, it's a moment in your future, as inevitable as next Tuesday. Black holes come in different sizes, and the size matters. A stellar mass black hole, the kind formed from a collapsed star, might weigh 10 or 20 times the mass of our Sun. Its event horizon would have a radius of a few dozen kilometers. You could fit one inside a large city. These are the smallest black holes we know about, and they're vicious. The tidal forces near them are extreme. Approach one, and you're dead before you realize what's happening. Then there are intermediate mass black holes, a poorly understood category sitting somewhere between stellar mass and supermassive. We've found hints of these, objects weighing hundreds or thousands of solar masses, but the formation mechanism is unclear. They might form from the collision and merger of stellar mass black holes, or from the direct collapse of very massive stars in the early universe. The data is thin. They're rare, or at least rarely detected. And then there are the supermassive black holes, the monsters, the ones that sit at the centers of galaxies and weigh millions or billions of times the mass of our Sun. These things are not formed from single collapsing stars. They can't be. No star is big enough. They were built over time, through accretion, through mergers, through a process that has been running since the universe was young. And nearly every large galaxy we've ever looked at has one, including ours. The black hole at the center of the Milky Way weighs about 4 million solar masses. 4 million. Take our sun and multiply it by 4 million. That's how much mass is sitting in a region smaller than the orbit of Mercury. Its event horizon has a radius of roughly 12 million kilometers. That's about 17 times the radius of our sun. 17 suns, lined up edge to edge, would just about span the diameter of that event horizon. For a long time, we didn't know it was there. We knew something was there. Astronomers had been mapping the center of the galaxy since the early 20th century, and the radio emissions from that region suggested something unusual. But confirming that it was a black hole required decades of patient observation. You can't see a black hole directly. By definition, it doesn't emit light. What you can see is the effect it has on nearby objects. Stars, gas, anything that gets close enough to feel its gravity. In the 1990s, two teams of astronomers began tracking individual stars near the center of the galaxy. They used some of the largest telescopes on Earth, instruments capable of resolving objects separated by fractions of an arcsecond on the sky, and they watched those stars move, not over days or weeks, over years, 16 years in one study. They measured positions, velocities, orbital paths. They built a map of how those stars were moving and worked backward to figure out what they were orbiting. The answer was unambiguous. The stars were orbiting an invisible object with a mass of about 4 million times the mass of our Sun, packed into a region so small that no other known object could fit. Not a cluster of stars, not a cloud of dark matter, not a dense clump of neutron stars, a black hole. That was the only explanation that survived the data. Reinhard Genzel, one of the astronomers who led that work, said the observations delivered the best empirical evidence that supermassive black holes do really exist. The mass at the center, he said, must be a black hole, beyond any reasonable doubt. For that work, Genzel shared the 2020 Nobel Prize in Physics. So we know it's there. We know how massive it is. We know where it is, about 26,000 light-years away in the direction of the constellation Sagittarius. We've even given it a name, Sagittarius A star. Sagittarius A star. The star symbol isn't decorative, it's astronomical notation indicating a compact radio source. The object itself doesn't shine, but the region around it does, faintly, in radio wavelengths, from the hot gas and magnetic fields swirling near the event horizon. That black hole, that 4 million solar mass knot in spacetime, has been sitting at the center of our galaxy for billions of years. We orbit it, not directly. We're 26,000 light-years out, tucked into one of the galaxy's spiral arms, circling the center at a leisurely 500,000 miles per hour. It takes us about 225 million years to complete one orbit. The black hole's gravity is only a tiny part of what holds the galaxy together. Most of the gravitational pull we feel comes from the combined mass of all the stars, gas and dark matter distributed throughout the Milky Way. But the black hole is there, anchoring the core, shaping the orbits of everything nearby. And for most of human history, we had no idea. We looked up at the night sky, traced the band of the Milky Way across the horizon, and never suspected that the faint glow in Sagittarius, barely distinguishable from the surrounding stars, marked the location of a monster. Black holes are not exotic, they're not rare. They are a natural consequence of gravity acting on mass. Build a star heavy enough, and when it dies, you get a black hole. Build a galaxy, and over time, a supermassive black hole assembles itself at the center. The universe makes these things routinely. By some estimates, our galaxy alone contains tens of millions of stellar mass black holes drifting quietly through the dark. Most of them will never interact with anything again. They'll just orbit the galaxy forever, invisible, patient, waiting for something to wander close enough to notice. The event horizon is a point of no return, yes, but it's also a boundary that protects the rest of the universe from whatever happens inside. A black hole is a cosmic sensor. It takes the most extreme physics imaginable, the collapse of matter into infinite density, the breakdown of space-time itself, and it wraps all of that in a one-way membrane that nothing can cross outward. Whatever madness is happening at the singularity stays at the singularity. The rest of the universe continues as if nothing happened, except it did happen, and the black hole is still there, bending space, warping time, holding entire galaxies together with gravity so strong that even light can't escape. We've defined what a black hole is. We've described the event horizon, the singularity, the geometry of curved space-time. Now we need to talk about the one we live with, the one sitting 26,000 light-years away, quietly anchoring the galaxy we call home. Because confirming its existence didn't just validate decades of theory. It forced us to accept that we've been living in orbit around a monster our entire history as a species, and we only just noticed. We've talked about black holes in theory. We've described the geometry, the event horizon, the mathematics of curved spacetime. Now we need to talk about the one we live with. The monster sitting at the center of our galaxy, anchoring the Milky Way, bending space around itself with a mass so absurd that for most of human history we couldn't even imagine it was there. Its name is Sagittarius A star. Sagittarius A with an asterisk, though nobody calls it that in conversation. Most astronomers shorten it to Skr E star, or just Sag A star, if they're in a hurry. The name comes from its location in the sky, roughly in the direction of the constellation Sagittarius, and the star notation marks it as a compact radio source, not a star, not remotely a star. But when radio astronomers first catalogued it decades ago, they didn't know what it was. They just knew something in that patch of sky was emitting radio waves, and the signal was coming from a point so small it might as well have been a star. It wasn't. What they had found was the radio signature of superheated gas swirling around a 4 million solar mass black hole. A hole in space 26,000 light-years away, sitting at the exact center of our galaxy, holding the Milky Way together in a way we didn't understand until embarrassingly recently. Let's start with the obvious question. How do you find the center of a galaxy when you're inside it? The Milky Way, seen from Earth, looks like a faint band of light stretching across the night sky. The ancient Greeks thought it looked like spilled milk, hence the name. For most of human history, nobody knew what it was. Some thought it was a glowing cloud. Others thought it might be a river of light, a crack in the heavens. It wasn't until the 1600s that Galileo pointed a telescope at it and realized the band was made of stars. Thousands of them, so densely packed that to the naked eye they blurred together into a continuous glow. By the early 1900s, astronomers had worked out that the Milky Way wasn't just a band of stars. It was the galaxy we lived in, seen edge-on from the inside. Our sun sits in one of the galaxy's spiral arms, about halfway out from the center, and when we look toward the densest part of the band, we're looking toward the galactic core. The brightest part of the Milky Way, the part that rises in the summer sky for observers in the northern hemisphere, points roughly in the direction of Sagittarius. That's where the center is, not visible as a single bright point. Not obvious in any way. just buried in the glow of a few 100 billion stars, hidden behind clouds of dust so thick that optical telescopes can't see through them. Dust is a problem. The center of the Milky Way is obscured by vast lanes of interstellar dust, tiny grains of carbon and silicates drifting in the space between stars. Visible light gets scattered and absorbed by that dust. Infrared light, with its longer wavelengths, can penetrate farther. Radio waves go right through. So if you want to study the galactic center, you can't use an optical telescope. You need infrared, you need radio, you need X-rays. And you need patience, because the center is 26,000 light-years away, which means even relatively large structures near the core appear as tiny, faint smudges on the sky. Radio astronomers started mapping the center in the 1950s and 60s. They found a bright, compact radio source sitting almost exactly where the geometric center of the galaxy should be. They called it Sagittarius A. Later observations resolved that source into multiple components, and the brightest, smallest one got the star designation, Sagittarius A star. For years, that's all it was, a radio blip, a curiosity, a point on a map. Then astronomers started looking at the stars. In the 1990s, two teams, one led by Reinhard Genzel at the Max Planck Institute in Germany, and the other by Andrea Ghez at UCLA, began a long-term project to track individual stars near the galactic center. Not just measure their positions once and move on. Track them, year after year, watch them move, map their orbits. This required some of the largest and most precise telescopes on the planet, infrared telescopes, because visible light couldn't punch through the dust. Adaptive optics, a technique that compensates for the blurring effects of Earth's atmosphere in real time, and a lot of patience. The stars they were tracking were close to Sagittarius A star, very close. Some of them were orbiting in elliptical paths that brought them within light hours of the radio source. These were not slow, distant orbits. These were tight, fast, violent loops. One star, later designated S2, completed a full orbit in just under 16 years. 16 years. For comparison, Pluto takes 248 years to orbit our Sun once. S2 was screaming around something at speeds that peaked above 5,000 kilometers per second. That's more than 1% of the speed of light. To make a star move that fast, you need gravity, a lot of gravity, and gravity comes from mass. By measuring the star's orbital period, its distance from the center, and the shape of its ellipse, you can calculate the mass of the object it's orbiting. The math is the same math that's been used since Kepler and Newton. Orbital mechanics. Plug in the numbers and out comes the answer. The answer was about 4 million times the mass of our Sun. 4 million, packed into a region smaller than our solar system. At those scales, there are only a few possibilities: a dense cluster of stars, a cloud of dark matter, a clump of neutron stars, or stellar mass black holes packed together, or a single supermassive black hole. The cluster option doesn't work. If you tried to cram 4 million solar masses worth of stars into a region that small, they'd collide, merge, and collapse into something even denser within a cosmically short time. The cluster would be unstable. Dark matter doesn't clump that tightly. We've never observed a dark matter concentration dense enough to produce the kind of gravitational effects seen at the galactic center. And dark matter doesn't emit radio waves or X-rays. A clump of stellar remnants, neutron stars or smaller black holes, has the same problem as the star cluster. Pack them that close and they merge. You'd end up with a supermassive black hole anyway, which leaves one option. The object at the center of the Milky Way, the thing the stars are orbiting, is a black hole, a single supermassive black hole weighing about 4.3 million times the mass of our Sun. Some more recent measurements refine that number to 4.297 million solar masses, give or take. The precision is absurd. We're talking about an object 26,000 light-years away, and we've measured its mass to better than 1% accuracy. Genzel and Ghez shared the 2020 Nobel Prize in Physics for this work. The Nobel Committee's citation said their observations provided the most convincing evidence for the existence of a supermassive black hole at the center of the Milky Way. Convincing is an understatement. The data doesn't leave room for anything else. But here's the strange part. Despite weighing 4 million times more than our Sun, Sagittarius A star is quiet, shockingly quiet. When astronomers look at other galaxies, especially distant ones, they often see incredibly bright cores. These are called active galactic nuclei, and they're powered by supermassive black holes that are actively feeding. Gas and dust spiral into the black hole, forming an accretion disk that heats up to millions of degrees and blazes across the electromagnetic spectrum. Some of these objects, called quasars, are so bright they outshine their entire host galaxies. The black hole at the center of a quasar might be no more massive than Sagittarius A star. The difference is how much it's eating. Sagittarius A star is barely eating anything, it's starving. Or more accurately, it's on a diet so strict that most of the time it's almost invisible. The accretion disk around it is faint. The X-ray emission is weak. For a black hole of its size, it should be much, much brighter. Observations suggest the black hole is accreting gas at a rate far below what the surrounding environment could supply. Most of the gas near the galactic center is too hot, too fast, or too poorly organized to fall in efficiently. It swirls around, emits a bit of radiation, and drifts away. Occasionally, something changes. Every so often, Sagittarius A star flares. The X-ray brightness jumps by a factor of a few dozen or more, then dies back down over the course of hours. These flares are thought to happen when a clump of gas, or maybe a small asteroid, gets close enough to be torn apart and consumed. The material spirals inward, heats up, glows briefly in X-rays, and then vanishes across the event horizon. The Chandra X Ray Observatory caught one of these flares in 2012. The temperature of the gas around the black hole spiked to tens of millions of degrees, and then within a few hours, it cooled and faded. That's about as dramatic as Sagittarius A star gets. The region immediately around the black hole, the part that's actually glowing faintly in radio and infrared, extends out maybe 5 to 30 light-years. That's tiny on a galactic scale. The Milky Way itself is about 100,000 light-years across. The black hole and its immediate neighborhood are a speck, a dot in the middle of a disk, and yet that dot contains more mass than 4 million suns. The event horizon of Sagittarius A star, the boundary beyond which nothing can escape, has a radius of about 12 million kilometers. For reference, that's roughly 17 times the radius of our Sun. If you lined up 17 suns edge to edge, they would just about span the diameter of that event horizon. It sounds enormous. On a human scale it is, but on a cosmic scale it's incredibly compact. You could fit the entire event horizon inside the orbit of Mercury with room to spare. We've been orbiting this thing our entire existence as a species and never noticed. The solar system takes about 225 million years to complete one orbit around the galactic center. We're moving at roughly 500,000 miles per hour, carried along by the combined gravity of all the stars, gas, and dark matter distributed throughout the Milky Way. Sagittarius A star contributes to that gravity, but it's not the dominant force holding us in orbit. Most of the gravitational pull we feel comes from the mass distributed throughout the galaxy. But the black hole is there, anchoring the core, shaping the orbits of stars that get close, bending space around itself in ways that nothing else in the galaxy can match. For decades, the existence of Sagittarius A star was inferred. We saw the radio emission, we tracked the orbits, we calculated the mass. We concluded it had to be a black hole, but we couldn't see it, not directly. Black holes, by definition, don't emit light. The best we could do was observe the gas and stars around it and work backward. That changed in May 2022. The Event Horizon Telescope, a global network of radio observatories working together as a single Earth-sized telescope, released the first image of Sagittarius A star, not the black hole itself. You can't photograph a black hole. What they photographed was the glowing ring of superheated gas orbiting just outside the event horizon. The shadow in the center, the dark circle, is the region where light can't escape. That shadow is the black hole's fingerprint. The proof that the event horizon is real, that the mass is concentrated exactly where the orbital data said it was. The image looks almost identical to the earlier image of the supermassive black hole at the center of the galaxy M87, which the Event Horizon Telescope released in 2019. A bright orange ring with a dark center. The ring is the accretion disk, the gas spiraling inward at a significant fraction of the speed of light, heated by friction and magnetic fields to temperatures high enough to glow in radio wavelengths. The dark center is the shadow of the event horizon. Light from the accretion disk curves around the black hole before reaching us, and some of it falls in and never comes back out. The result is a dark circle, slightly larger than the actual event horizon because of gravitational lensing, surrounded by a bright halo. Getting that image of Sagittarius A star was harder than imaging M87 star. M87 star is much farther away, sitting in a galaxy 55 million light-years from Earth, but it's also much more massive, weighing about 6.5 billion solar masses. That size makes it relatively stable. The gas around it orbits over the course of days or weeks, which means the structure of the accretion disk doesn't change much during a single night of observation. Sagittarius A star is smaller and closer, and the gas around it moves faster, much faster. The orbital period of material near the event horizon is measured in minutes, not days. That means the structure of the accretion disk is constantly shifting. During the hours it took the Event Horizon Telescope to gather data, the gas around Sagittarius A star changed shape, flickered, and rearranged itself. Getting a clean image required stitching together multiple observations and using sophisticated algorithms to average out the variability. The result is less a photograph and more a statistical reconstruction. But it's real. The ring is there, the shadow is there, and the size of that shadow matches the predictions from general relativity almost exactly. There is something deeply unsettling about having a picture of the black hole at the center of our galaxy. For all of human history, we looked up at the Milky Way and saw beauty, a glowing river of stars, a band of light cutting across the night. We gave it names, built myths around it, used it to navigate, and the entire time, at the heart of that river, there was a mouth, a 4 million solar mass knot in space-time that has been sitting there for billions of years, bending space, swallowing anything that gets too close, defining the structure of the galaxy around it, and we never suspected. Not because we weren't looking, because we didn't have the tools. The dust blocked the view, the distances were too great, the orbits took decades to map. Only in the last 30 years, after centuries of astronomy, did we finally gather enough data to confirm what was there. A monster. Dormant, quiet, almost polite in how little attention it draws to itself, but a monster nonetheless. Sagittarius A star is not unique. Nearly every large galaxy we've observed has a supermassive black hole at its center. Some are more active than ours. Some are feeding voraciously, blazing across the universe as quasars. Some are larger, much larger. But they're all there, sitting at the cores, shaping the galaxies around them in ways we're still working out. The relationship between a galaxy and its central black hole is one of the biggest open questions in astrophysics. Do black holes form first and seed the galaxy around them, or do galaxies form first and build black holes at their centers over time? The answer is probably both, depending on when and where you're looking in the history of the universe. What we know for certain is that our galaxy has 4.3 million times the mass of our Sun, 26,000 light-years away in the direction of Sagittarius, a radio-bright point surrounded by fast-moving stars and faint superheated gas. An event horizon 12 million kilometers across, wrapped around a singularity that physics can't fully describe. A permanent scar in space-time that we've been orbiting for as long as the solar system has existed. The discovery of Sagittarius A star didn't just confirm that supermassive black holes exist. It forced us to accept that we live in a galaxy with one. That every time we look up at the Milky Way, we're looking at a structure held together in part by an object we can't see, can't visit, and barely understand. An object that bends space so sharply that nothing, not even light, can escape once it crosses the event horizon. And that brings us to the next question. What would it actually be like to approach that boundary? To fall toward a black hole, to cross the event horizon, to experience firsthand the geometry we've been describing in theory. Because theory is one thing, math is one thing. But if you want to understand what a black hole really is, you need to imagine what happens at the edge, where time breaks, where space tilts, where every possible future points inward and there is no way back. We've established what Sagittarius A star is: 4 million solar masses packed into a region smaller than our solar system, sitting 26,000 light-years away at the center of our galaxy. We've talked about the event horizon, the boundary where escape velocity exceeds the speed of light. We've described it as a one-way membrane, a point of no return. Now we need to talk about what it would actually be like to approach that boundary, to fall toward a black hole, to cross the event horizon, to experience firsthand the geometry we've been describing in equations and abstractions. This is not a trip anyone will ever take. Let's be clear about that up front. Any spacecraft we could build would be vaporized long before reaching the event horizon, torn apart by tidal forces or fried by radiation from the superheated gas swirling around the black hole. And even if you could somehow survive the approach, the trip is one way. There is no coming back. No rescue, no clever engineering solution that lets you reverse course once you've crossed. The event horizon is the universe's most absolute boundary. Cross it and you are gone. But hypothetically, if you could make the journey, if you had a magic spacecraft that could shield you from radiation and tidal forces and keep you alive long enough to observe what was happening, here's what you would experience, and here's what someone watching you from a safe distance would see. Because those two perspectives, yours and theirs, would tell completely different stories about the same event. Both stories would be true. That's relativity for you. Let's start with the setup. You're in a spacecraft, falling toward Sagittarius A star. Not orbiting, falling. You've shut off your engines and you're dropping straight toward the event horizon. For the sake of this thought experiment, We'll assume you're falling from far enough away that your initial velocity is low. Gravity will do the work. The black hole weighs 4 million times the mass of our Sun. Its pull is strong enough that by the time you get close, you'll be moving at a significant fraction of the speed of light. At first, nothing looks unusual. Space around you seems normal. The stars behind you look like stars. The darkness ahead is just darkness. Sagittarius A star itself is invisible. Black holes don't glow. What little light there is comes from the faint accretion disk, the thin haze of superheated gas orbiting just outside the event horizon. It's not much. Certainly not bright enough to illuminate your spacecraft. You're falling through the dark towards something you can't see, guided only by instruments telling you that the gravitational pull is increasing. As you fall, you start to notice something strange. Time is behaving oddly. Not for you. Your watch ticks normally. Your heart beats at its usual rate. If you check your pulse, it's fine. If you look at a clock on the wall of your spacecraft, it reads the same as it always has. Locally, time flows exactly as you'd expect. But when you look at the signal from your mission control, the people who launched you on this one-way trip, their transmissions are coming in faster than they should. Their voices sound higher pitched. The timestamps on their messages are accelerating. What should be 1 second of their time is passing in less than 1 second of yours. You are experiencing time dilation. Time runs slower in a strong gravitational field. That's one of the predictions of general relativity, and it's been confirmed over and over again in experiments here on Earth. Clocks at sea level tick slightly slower than clocks on mountaintops. GPS satellites have to correct for the fact that time runs faster in orbit than it does on the ground. Near a black hole, the effect becomes extreme. The closer you get to the event horizon, the more dramatically time tilts. From your perspective, falling inward, you're still experiencing time normally, but relative to the outside universe, you're moving through time more slowly. The universe outside is speeding up. If you look back at the stars behind you, they start to look strange. The light from distant galaxies, which has been traveling toward you for billions of years, is now getting compressed, blue-shifted. The wavelengths are shortening, shifting toward the blue end of the spectrum and beyond. Ultraviolet, X-rays. If you could see in those wavelengths, the universe behind you would be getting brighter and more energetic. Ahead of you, toward the black hole, everything is dark. There's nothing to see. The event horizon doesn't emit light, and the faint glow from the accretion disk is behind you now. You're falling into absolute blackness. Your spacecraft is accelerating, not because you're firing engines, because gravity is pulling you inward, and there's nothing to slow you down. By the time you're within a few event horizon radii of Sagittarius A star, you're moving at tens of thousands of kilometers per second, a decent fraction of light speed. At this point, if you wanted to turn around, you couldn't. Not because you've crossed the event horizon yet, you haven't, but because the amount of thrust you'd need to escape has become absurd. You'd need to accelerate to faster than the local escape velocity, and that velocity is climbing toward the speed of light. No rocket we've ever built, no propulsion system we've ever imagined could generate that kind of thrust. You're committed. The fall will continue. Now let's switch perspectives. Let's talk about what Mission Control is seeing. The people who launched you. The ones watching from a safe distance, far from the black hole's influence, tracking your spacecraft with telescopes and waiting for your transmissions. What they see is very different from what you're experiencing. As you fall toward the event horizon, they see you slow down. Not because you've hit the brakes, because the light coming from your spacecraft is climbing out of a deeper and deeper gravitational well, and that climb costs energy. The photons get redshifted, stretched to longer wavelengths. Red light becomes infrared. Infrared becomes radio waves. Your image dims. The signals from your spacecraft, the telemetry, the video feed, start arriving slower and slower. What should take 1 second to transmit starts taking 2 seconds, then 10, then 100. From mission control's perspective, you never quite reach the event horizon. You get closer and closer, but the last few meters take longer and longer. Your image freezes at the edge, redshifted into invisibility, stretched and dimmed until there's nothing left to see. The last photon that escapes from your spacecraft before you cross the horizon takes an infinite amount of time, from their perspective, to reach them. You appear to be frozen at the edge of the black hole forever, stuck. Time, for you, has effectively stopped, as seen from the outside. Both perspectives are correct. That's the part that breaks intuition. You, falling inward, cross the event horizon in a finite amount of your time. Let's say it takes you 1 hour from the moment you pass some arbitrary outer marker until you cross the horizon. 1 hour on your watch. You experience every second of that hour. You cross. You keep falling. From your perspective, nothing magical happens at the horizon itself. There's no barrier, no wall, no sign saying you are now entering a black hole. You just keep moving inward, following the straightest path through increasingly curved space. But to mission control, watching from outside, you never cross. You approach the horizon asymptotically, getting closer and closer, but never quite arriving. They lose your signal, you fade from view. But mathematically, from their frame of reference, you're still out there, frozen at the edge. Your last transmitted photon stretched to infinite wavelength, taking infinite time to climb out of the gravitational well. This is not a disagreement about the facts. It's a disagreement about reference frames. Time is not absolute. It flows at different rates depending on where you are and how fast you're moving. Near a black hole, that difference becomes extreme, infinite even, in the limit as you approach the horizon. The universe outside speeds up relative to you. You slow down relative to it. Both descriptions are true simultaneously. There's a theoretical wrinkle here that physicists have been arguing about for years. It's called the firewall paradox. The basic question is this: if you fall across the event horizon, should you feel anything? General relativity says no. The equivalence principle, one of the core ideas of relativity, says that freely falling in a gravitational field is locally indistinguishable from floating in empty space. You shouldn't feel any force. The event horizon, according to classical general relativity, is not a special place. It's just a coordinate boundary. Cross it, and nothing dramatic happens. You keep falling. But quantum mechanics complicates that picture. In the 1970s, Stephen Hawking showed that black holes aren't entirely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation carries energy away from the black hole, meaning the black hole slowly loses mass over time. Eventually, it evaporates. That process raises a problem. Hawking radiation is thermal. It's random. It doesn't carry information about what fell into the black hole. But quantum mechanics says information can't be destroyed. If you throw a book into a black hole, the information in that book, the arrangement of atoms, the words on the pages, has to be preserved somewhere. If the black hole evaporates into random thermal radiation, where did the information go? One proposed solution is that the information is somehow encoded on the event horizon itself, smeared across the surface in a way that allows it to eventually escape as the black hole evaporates. But if that's true, if the event horizon is doing something active to preserve information, then it can't be an empty, unremarkable boundary. It has to be doing something, and that something, according to some calculations, might be violent. A wall of high-energy particles, a firewall. Cross the event horizon, and instead of smoothly continuing your fall, you'd be incinerated instantly by a blast of radiation. This is the firewall paradox. Either general relativity is wrong, and the event horizon is a violent place, or quantum mechanics is wrong, and information can be destroyed, or there's some third option that we haven't figured out yet. As of now, the paradox is unresolved. Most physicists suspect there's no actual firewall, that general relativity is correct and the horizon is smooth. But the paradox highlights how little we understand about the intersection of quantum mechanics and gravity. Black holes sit right at that intersection, and the math gets messy. For the sake of this thought experiment, let's assume the firewall doesn't exist. Let's assume general relativity holds and the event horizon is smooth. You cross it, you're still alive, your spacecraft is intact. You look around. Behind you, where the universe used to be, you see something strange. The stars you were watching, the galaxies, mission control, all of it is compressed into a shrinking circle of light above you. The light from the outside universe is still reaching you, but it's being bent by the extreme curvature of space around the black hole. Everything outside is visible in a cone that narrows as you fall deeper. The rest of the sky is black, not the black of empty space, the black of nothing. The event horizon is behind you now, between you and the outside universe, and no light from deeper inside can escape outward. There's nothing to see in that direction, just void. You're still accelerating, still falling. The gravitational pull is increasing, and now the tidal forces start to matter. Tidal forces are the difference in gravitational pull between your head and your feet, or between the front of your spacecraft and the back. Gravity gets weaker with distance, that's always true, but near a black hole, the gradient becomes steep, very steep. If you're falling feet first, your feet are closer to the center of the black hole than your head. They experience stronger gravity. The difference in pull stretches you. At the same time, gravity pulls you inward from all sides, compressing you laterally. The result is that you get longer and thinner, stretched like a piece of taffy. This process has a name, and it's not a joke. Physicists call it spaghettification. You become a noodle. For a stellar mass black hole, the kind that forms from a collapsed star, spaghettification happens outside the event horizon. You'd be torn apart before you ever crossed. But Sagittarius A star is a supermassive black hole, 4 million times the mass of the Sun. Its event horizon is huge, tens of millions of kilometers across. And because the event horizon is so large, the tidal gradient at the horizon itself is relatively gentle. You could cross the event horizon of a supermassive black hole intact. You'd still die, but you'd have time, minutes maybe, possibly longer, depending on exactly how massive the black hole is and how far you are from the center. As you fall deeper, the tidal forces grow, the stretching becomes stronger. Your spacecraft starts to creak, then groan, then deform. If you're still conscious, you'd feel it, a pulling sensation. Not painful at first, just uncomfortable, a sense that your body is being drawn out, lengthened. The sensation would intensify. Within minutes, the forces would overcome the structural integrity of your spacecraft. It would crack, split. The pieces would separate, each following its own geodesic toward the center. You'd be in free fall now, no protection, no hull, just your body stretched and compressed by gravity gradients so extreme that molecular bonds start to fail. This is where the journey ends for anything made of matter. The tidal forces eventually exceed the strength of atomic bonds. You don't stay intact as a human. You don't even stay intact as a collection of cells. You become a stream of atoms, a thin line of disconnected particles, all falling toward the center, spaghettified. The stretching continues until you're effectively one atom wide and absurdly long, a thread of matter spiraling inward, and then even that thread is pulled apart as you approach the singularity at the very center. The singularity, where all the mass of the black hole is concentrated, where space-time curvature becomes infinite, where the equations break down and nobody knows what actually happens. You don't experience the singularity, not in any meaningful way. By the time the tidal forces are strong enough to rip you into atoms, you're long dead. Your consciousness, whatever that is, requires structure, neurons, synapses, chemistry. All of that stops functioning long before you reach the singularity. What reaches the center is not you. It's a diffuse cloud of particles that used to be you, falling into a point of infinite density that general relativity describes but doesn't fully understand. From the perspective of the outside universe, none of this has happened yet. You're still frozen at the event horizon, your image dim and redshifted, stuck in time. But from your perspective, from the reference frame of the infalling atoms that were once a person, the journey took minutes, finite time, a measurable duration. You crossed the horizon, you fell. You were destroyed. And now you're part of the black hole, added to its mass, increasing its event horizon radius by an imperceptibly small amount. There is no coming back. This is worth repeating because it's the single most absolute fact about black holes. The event horizon is a one-way boundary. Once you cross, every possible future trajectory points inward, not because you're being pulled, because the geometry of space-time itself has been bent so sharply that outward is no longer a direction you can move in. You can fire your rockets, you can accelerate, you can struggle, doesn't matter. The math is unambiguous. Inside the event horizon, all paths lead to the singularity. It's not a place you're traveling to, it's a moment in your future, as inevitable as tomorrow. Here's the part that should bother you. The event horizon is not a physical barrier. There's no surface, no shell. If you were falling across it, you wouldn't feel anything special. Locally, space would seem normal, but once you've crossed, the rest of the universe is gone, not hidden, gone. You can't send a signal out. You can't see anything outside except the rapidly shrinking cone of light from the universe you left behind. You are cut off, isolated, sealed inside a region of space-time that no longer communicates with the outside, and yet from the outside you never crossed. Your image is still there, frozen at the edge, stretched and dimmed but never quite vanishing. Both descriptions are correct. You crossed. You didn't cross. You died. You're still there. The contradiction is built into the geometry. Time doesn't flow at the same rate everywhere. What happens, when it happens, depends on who's asking. Black holes are the universe's ultimate sensors. Whatever happens at the singularity, whatever physics governs that region of infinite curvature and broken equations, stays hidden behind the event horizon. The rest of the universe never sees it, can't see it. The event horizon is a one-way filter that allows matter and energy to fall in, but prevents any information from coming back out. This is probably a good thing. If singularities were naked, if you could observe a region where the laws of physics genuinely break down, the universe would have a problem. Causality might fail. Predictions would become impossible. General relativity allows for singularities, but it also seems to demand that they be hidden. So far, every black hole we've observed follows that rule. Sagittarius A* sits at the center of our galaxy, right now, with an event horizon spanning tens of millions of kilometers. Anything that crosses that boundary is gone. Stars that wander too close get torn apart by tidal forces before they reach the horizon, their gas stretched into thin streams that spiral inward and vanish. Asteroids, comets, clouds of dust, all consumed. And over billions of years, the black hole grows, slowly, one swallowed star at a time, one accreted gas cloud at a time, adding mass, expanding its event horizon outward by tiny increments. That growth is the key to understanding the next part of the story, because Sagittarius A star didn't start out weighing 4 million solar masses. No star is massive enough to collapse into a black hole that size. It started smaller, much smaller, and over the lifetime of the galaxy, it's been growing, feeding, merging with other black holes, building itself up from something modest into the monster we see today. And that process, the process of black hole growth, turns out to be intimately connected to how galaxies themselves form and evolve. Supermassive black holes don't just sit at the centers of galaxies, they shape them, they regulate star formation, they heat the gas in the galactic core. They eject matter at near light speed in jets that stretch for thousands of light years. The relationship between a galaxy and its central black hole is one of the most important unsolved problems in astrophysics, and the only way to understand that relationship is to look at how black holes grow, how they feed, how they interact with the galaxies around them, how they went from stellar mass remnants weighing a few dozen suns to supermassive monsters weighing millions or billions. Sagittarius A star sits at the center of our galaxy right now, weighing 4 million times the mass of the Sun, anchoring the Milky Way, bending space around itself in ways that nothing else in the galaxy can match. We've talked about what it is. We've described the event horizon. We've walked through what would happen if you fell toward it. Now we need to talk about where it came from. Because black holes that size don't form from single collapsing stars. They can't. No star is massive enough to leave behind a 4 million solar mass remnant when it dies. Sagittarius A star was built, slowly, over billions of years, through a process that turns out to be intimately connected to how galaxies themselves assemble and evolve. This is where the story gets strange, because supermassive black holes aren't just passengers sitting at the centers of galaxies, doing nothing but quietly holding a few nearby stars in orbit. They're active participants. They shape the galaxies around them. They regulate star formation. They heat gas. They eject matter at near light speed in jets that stretch for thousands of light years. And the relationship between a galaxy and its central black hole is so tight, so consistent across the universe, that it can't be a coincidence. Something about the way galaxies grow is tied directly to the way their central black holes grow. The two processes are linked. And for decades, astronomers have been trying to figure out how. The most obvious question is the first one. How do you build a black hole that weighs millions of times the mass of the Sun? Stellar mass black holes form from collapsing stars. We covered that. A massive star runs out of fuel, the core collapses, you get a supernova, and if the core is heavy enough, what's left behind is a black hole weighing maybe 10 or 20 solar masses. That process is well understood, but it doesn't scale. You can't start with a 10 solar mass black hole and just feed it until it weighs 4 million. The math doesn't work, not in the time available. Black holes grow by accretion. They swallow gas, dust, stars, anything that gets close enough. But there's a limit to how fast they can grow. When matter falls toward a black hole, it doesn't drop straight in. It spirals, it forms an accretion disk, and that disk gets hot. Very hot. Hot enough to glow, hot enough to emit radiation across the electromagnetic spectrum. That radiation pushes outward on the surrounding gas, creating pressure that resists further infall. The result is a natural speed limit on how fast a black hole can grow. Physicists call it the Eddington limit. If a black hole tries to eat faster than the Eddington limit allows, the radiation pressure from the infalling matter blows away the surrounding gas, shutting off the food supply. The Eddington limit depends on the mass of the black hole. Bigger black holes can accrete faster. But even at the maximum rate, even if a black hole is feeding as efficiently as physics allows, it takes time to grow, a lot of time. If you start with a 10 solar mass black hole and let it feed at the Eddington limit continuously, it would take hundreds of millions of years to reach 1 million solar masses. To reach 4 million would take longer. To reach 1 billion, the kind of mass we see in the supermassive black holes powering distant quasars, you'd need more time than the early universe had, and that's the problem. Because we've found supermassive black holes in the early universe, very early. Quasars powered by black holes weighing billions of solar masses, shining when the universe was less than 1 billion years old, less than 10% of its current age. Those black holes shouldn't exist. Not if they started as stellar mass remnants and grew by accretion. There wasn't enough time. So either black holes in the early universe were feeding faster than the Eddington limit, which requires some exotic mechanism we don't fully understand, or they didn't start small. Maybe they started big. Maybe, in the chaotic conditions of the early universe, massive clouds of gas collapsed directly into black holes weighing thousands or even hundreds of thousands of solar masses, skipping the stellar phase entirely. These hypothetical objects are called direct collapse black holes, and if they existed, they would give supermassive black holes a huge head start. Grow from 100,000 solar mass seed instead of a 10 solar mass seed, and suddenly the timeline works. Nobody knows if direct collapse black holes are real. The conditions required are extreme. You need a massive cloud of primordial gas, mostly hydrogen and helium, with almost no heavier elements. Heavier elements cool gas efficiently, allowing it to fragment into stars. Without them, the cloud stays hot, resists fragmentation, and if it's massive enough, it can collapse straight into a black hole. The early universe had plenty of pristine gas. Whether it collapsed the right way, in the right places, often enough to explain the supermassive black holes we see, is still an open question. There's a third option: mergers. Black holes can grow by colliding with and absorbing other black holes. In the dense cores of young galaxies, where stars are packed close and black holes are drifting through the chaos, mergers would have been common. Two stellar mass black holes collide. You get a black hole twice as heavy. That black hole collides with another. You get one 4 times as heavy. Repeat the process enough times and you can build something massive. This process is slow, but it doesn't hit the Eddington limit because it's not accreting gas. It's directly adding mass. The real answer is probably all three. Some combination of stellar mass seeds, direct collapse, and mergers, all happening in the messy, violent cores of young galaxies. The early universe was a different place. Star formation was more intense. Gas was denser. Galaxies were smaller, more chaotic, colliding and merging constantly. In that environment, black holes had every opportunity to grow fast, and grow they did. By the time the universe was a few billion years old, supermassive black holes were everywhere. Nearly every large galaxy had one, and the mass of the black hole was weirdly consistent with the mass of the galaxy itself. Not the whole galaxy, just the central bulge. The dense, roughly spherical region of stars at the galaxy's core. Measure the mass of the bulge, and you can predict the mass of the black hole. The ratio is about 1 to 1,000. For every solar mass in the bulge, the black hole weighs about 1,000th of that. The relationship holds across galaxies of wildly different sizes, from dwarfs to giants, across billions of light years and billions of years of cosmic history. This is not a coincidence. When you see a correlation that tight, that consistent, something is causing it. The black hole and the galaxy are not evolving independently. They're talking to each other, influencing each other, growing together. The question is how. The answer seems to be feedback, energy. When a black hole feeds, when gas spirals into the accretion disk and heats up, it doesn't just glow. It erupts, it launches jets, it blows winds. It pumps enormous amounts of energy into the surrounding gas, heating it to temperatures so high that it can't collapse to form stars. This process, black hole-driven feedback, is one of the most important mechanisms regulating star formation in galaxies. Here's how it works. A young galaxy forms from collapsing clouds of gas. That gas cools, fragments, and starts forming stars. Some of those stars are massive. They live fast, die young, and leave behind black holes. Those black holes sink to the center of the galaxy, merge, and start growing. As the black hole grows, it pulls in more gas. The gas forms an accretion disk. The disk heats up, radiation pours out. Some of that radiation is absorbed by the surrounding gas, heating it and driving it outward in powerful winds. At the same time, magnetic fields threading the accretion disk can launch narrow jets of matter moving at close to the speed of light. Those jets punch through the galaxy, carrying energy far from the center, heating the gas in the outer regions. The result is that star formation slows. Gas that would have collapsed to form stars is now too hot. It's been heated by the black hole. The galaxy stops growing as quickly. The black hole, meanwhile, has eaten its way through much of the available gas near the center. The feeding slows, the feedback weakens, and the galaxy settles into a more stable state. Older, quieter, less active. This is the phase most large galaxies are in today, including the Milky Way. The black hole is still there, the galaxy is still there, but the fireworks are over. This feedback mechanism explains the correlation between black hole mass and bulge mass. If the black hole grows too fast, it heats the surrounding gas so much that star formation shuts off entirely. The galaxy stops growing, the black hole stops feeding, the system self-regulates. The black hole and the galaxy grow together, each limiting the other's growth, until they reach an equilibrium. That equilibrium is what we see when we measure galaxies today. A tight, consistent relationship between the mass of the black hole and the mass of the stars in the central bulge. Sagittarius A star fits this picture perfectly. It weighs about 4 million solar masses. The bulge of the Milky Way weighs a few tens of billions of solar masses. Divide one by the other and you get roughly 1,000th. Right on the curve. Our galaxy, like most galaxies, has a black hole that's exactly the size you'd expect if feedback regulated its growth. But Sagittarius A star is quiet now. It's accreting gas at an absurdly low rate, only a few hundredths of an Earth mass per year. Compare that to the black holes powering quasars, which are swallowing hundreds or thousands of Earth masses per year, and you see the difference. Sagittarius A star is starving. Or more accurately, it's finished feeding. It ate its fill billions of years ago, and now it's coasting. Occasionally, a stray cloud of gas or a torn-apart asteroid falls in, and the black hole flares briefly in X-rays. But most of the time, it's dormant. This dormant phase is typical for galaxies in the present-day universe. Most supermassive black holes are quiet. They've run out of easily accessible gas. The galaxies around them have settled into stable configurations where star formation is slow and the central black hole has nothing left to eat. But it wasn't always this way. In the early universe, things were very different. Quasars are what happens when a supermassive black hole feeds violently. The name is short for quasi-stellar object, because when astronomers first discovered them in the 1960s, they looked like stars, bright, point-like sources of light. But their spectra were bizarre. The emission lines were shifted so far to the red that it was clear these objects were incredibly distant. And if they were distant and still appeared bright, they had to be absurdly luminous. Some quasars shine with the light of 1,000 galaxies, 1,000. All that light coming from a region smaller than our solar system. The only thing that can produce that much energy in that smaller space is a supermassive black hole feeding at close to the Eddington limit. Gas pouring into the accretion disk, heating to millions of degrees, glowing so brightly that it outshines every star in the host galaxy combined. Quasars are the most luminous, persistent objects in the universe, and they were most common when the universe was young. Between 1 and 3 billion years after the Big Bang, quasars were everywhere. Hundreds of them scattered across the sky, each one marking a galaxy in the throes of violent growth. As the universe aged, quasars became rarer. By the time the universe was 5 or 6 billion years old, most of them had faded. The black holes had eaten the available gas. The galaxies had settled. Today, quasars are uncommon. Most supermassive black holes are in their quiet phase, like Sagittarius A star, accreting at a trickle and producing almost no light. But the connection is clear. Quasars are not a different kind of object. They're the same supermassive black holes we see in present-day galaxies, caught in an earlier, more energetic phase of their lives. Every large galaxy went through a quasar phase, including ours. That means Sagittarius A star was once a quasar. Billions of years ago, when the Milky Way was younger and gas was abundant, the black hole at the center was feeding voraciously. The accretion disk would have been bright enough to outshine the entire galaxy. Jets might have been launched, carving through the surrounding gas, heating it, driving it outward. Star formation in the central regions would have been suppressed by the energy pouring out of the black hole. And then, over time, the gas ran out, the feeding slowed, the quasar phase ended, the black hole went quiet. And the galaxy we see today, with its slow, steady star formation and its dormant central black hole, is what was left behind. This picture, black holes regulating galaxy growth through feedback, has become the standard model in astrophysics. It's not without problems. The details of how feedback works are still being worked out. How exactly do jets heat gas? How much energy needs to be injected to shut off star formation? How does the black hole know when to stop growing? These are active areas of research, but the broad outline is clear. Supermassive black holes and galaxies grow together. The black hole feeds, heats the gas, limits star formation, and in doing so, limits its own growth. The result is the tight correlation we see between black hole mass and galaxy mass. A relationship so consistent it shows up in galaxies across the entire observable universe. There's a broader implication here that's worth pausing on. Black holes are not just destroyers. They're not cosmic vacuum cleaners mindlessly swallowing everything in reach. They're regulators, architects. The energy they pump into their surroundings shapes the galaxies around them, determining how many stars form, how the gas is distributed, how the galaxy evolves. Without supermassive black holes, galaxies would look different. They'd be more gas-rich. Star formation would be more chaotic. The central regions would be denser, more crowded. Black holes, by heating and ejecting gas, prevent that. They impose order, structure. They're builders as much as they are destroyers. This is a shift in how we think about black holes. For most of their history in popular imagination, black holes were monsters, cosmic threats, objects that consumed everything and gave nothing back. And on a local scale, that's still true. Fall into a black hole and you're gone. No escape, no second chances. But on a galactic scale, the picture is more complicated. Black holes don't just take, they give back. They return energy to their surroundings. They regulate, they shape, they build the structures we see in the universe today. Sagittarius A star is one of millions of supermassive black holes scattered across the universe. Every large galaxy has one. Some are bigger, some are more active, but they're all there, sitting at the centers, anchoring the cores, shaping the galaxies around them through feedback and accretion. And the process that built them, the slow accumulation of mass through billions of years of feeding and merging, is the same process that built the galaxies themselves. The two are inseparable. You can't understand galaxies without understanding black holes. And you can't understand black holes without understanding the galaxies they live in. The correlation between black hole mass and galaxy mass is one of the tightest relationships in all of astrophysics. It holds across 6 orders of magnitude in mass. From dwarf galaxies with black holes weighing a few 100,000 solar masses to giant ellipticals with black holes weighing tens of billions, the ratio stays roughly constant, about 1 part in 1,000. That consistency is a signature. It's the universe telling us that these two objects, the black hole and the galaxy, are not independent, they're coupled, they're part of the same system, and that system has been running for most of the history of the universe. Supermassive black holes have been growing and shaping galaxies for more than 10 billion years. They were there in the early universe, powering quasars, regulating the first generations of stars. They were there in the Middle Ages of the cosmos, when galaxies were colliding and merging and star formation was at its peak. And they're here now, in the present-day universe, mostly quiet, mostly dormant, but still holding galaxies together, still shaping the structures we see when we look out into the night sky. Sagittarius A star is not unique. It's typical, a standard-issue supermassive black hole in a standard-issue spiral galaxy. 4 million solar masses, quiet, starving, sitting at the center, bending space, anchoring the Milky Way. It's been there for billions of years. It will be there for billions more. And every time we look at it, every time we measure the orbits of nearby stars, or catch a flare in X-rays, or reconstruct an image of the glowing ring around its event horizon, we're looking at a piece of the machinery that built the galaxy we live in. The discovery that black holes shape galaxies is one of the most important shifts in modern astrophysics. It changed the narrative. Black holes went from being exotic endpoints of stellar evolution, curiosities at the edge of physics, to being central players in the story of how the universe assembled itself. They're not passive, they're not inert, they're active, they're regulatory, they're essential. And the only reason we know any of this is because we've been watching them, measuring them, tracking the stars around Sagittarius A star, observing quasars across billions of light years, mapping the correlation between black hole mass and galaxy mass, simulating feedback in supercomputers, building models, testing predictions. Every observation, every data point adds another piece to the puzzle. And the puzzle that's emerging is stranger and more elegant than anyone expected. Black holes aren't monsters, they're sculptors. They're the tools the universe uses to shape galaxies, to regulate star formation, to build the structures we see today. But there's a problem. We can't see black holes directly. By definition, they don't emit light. Everything we know about them comes from indirect observation. from the light of gas swirling around them, from the orbits of nearby stars, from the gravitational waves they produce when they merge, from the radio emissions of their jets. Black holes are invisible, and if you want to study an invisible object, you need to get creative. You need to look for the echoes, the fingerprints, the effects they have on the things around them. And that means developing techniques to detect black holes even when you can't see them. Techniques that have gotten so sophisticated, so precise, that we can now map black holes across the universe, measure their masses, track their growth, and even, in a few cases, take their picture. We've talked about how black holes shape galaxies, how they regulate star formation through feedback, how they grow by feeding on gas and merging with other black holes. We've described Sagittarius A star, the 4 million solar mass monster sitting at the center of the Milky Way, anchoring our galaxy, bending space around itself in ways that nothing else can match. But here's the part that should bother you. For all the detail we've covered, for all the measurements and orbital calculations and images, nobody has ever actually seen a black hole. Nobody can. By definition, black holes don't emit light. They're black. The event horizon is a one-way membrane. Light crosses inward and never comes back out. So if you point a telescope at a black hole, any telescope, optical or infrared or ultraviolet, you see nothing. Darkness. A hole in the sky where something massive is sitting but refusing to glow. For most of human history, that would have been the end of the story. Can't see it, can't study it, move on. But astronomers are stubborn. And over the last century, they've developed an entire toolkit for finding invisible objects, for detecting things that don't emit light by watching what they do to the things around them, for reading the echoes and fingerprints that black holes leave behind even when the black holes themselves stay hidden. This is how we know Sagittarius A star exists. This is how we've mapped tens of millions of stellar mass black holes scattered through the Milky Way. This is how we've confirmed that nearly every large galaxy in the universe has a supermassive black hole at its center, not by seeing them directly, by watching them bend space, heat gas, pull stars into impossible orbits, and in one recent case, by taking a picture of the glowing ring of matter swirling just outside the event horizon. The black hole itself is still invisible, but the shadow it casts is not. Let's start with the simplest method, the one that confirmed Sagittarius A star in the first place. Watch the stars. In the 1990s, two teams of astronomers began a project that would take decades to complete. Reinhard Genzel at the Max Planck Institute in Germany and Andrea Ghez at UCLA pointed infrared telescopes at the center of the Milky Way and started tracking individual stars near the galactic core, not measuring their positions once and walking away, tracking them year after year, watching them move, mapping their orbits. This required patience on a scale that's hard to overstate. Stars near the galactic center are faint, obscured by dust, packed so densely that separating one from another takes instruments with extraordinary resolution, and the orbits themselves take years to trace. Some of them take decades, but the payoff was worth it. One star in particular, later designated S2, became the key. S2 orbits something at the very center of the galaxy in a tight ellipse that brings it within light hours of the core. The orbit takes just under 16 years to complete. 16 years. For comparison, Pluto takes 248 years to orbit our Sun once. S2 is moving fast. At its closest approach, it's traveling at more than 5,000 kilometers per second. That's 1.5% of the speed of light. Nothing makes a star move that fast except gravity. Enormous gravity. and gravity comes from mass. By measuring the orbital period, the distance from the center, and the shape of the ellipse, you can calculate the mass of the object the star is orbiting. This is basic orbital mechanics, the same math Kepler used in the 1600s to describe planetary motion. Plug in the numbers and the answer comes out clean. The object at the center weighs about 4 million times the mass of our Sun. 4 million. And it's packed into a region only about 100 astronomical units across. 1 astronomical unit is the distance from the Earth to the Sun. 100 astronomical units is roughly twice the distance from the Sun to Pluto. That's tiny. Absurdly tiny for something weighing 4 million solar masses. What could it be? Not a cluster of stars. If you tried to cram 4 million solar masses worth of stars into a region that small, they'd collide and merge within a cosmically short time. The cluster would be unstable, not dark matter. Dark matter doesn't clump that tightly, and even if it did, it wouldn't produce the radio emissions coming from the center. Not a collection of neutron stars or smaller black holes. Pack them that close and they'd merge into a single object, a supermassive black hole. That's the only option left. The only object physics allows that can pack that much mass into that smaller space without immediately collapsing or exploding or radiating itself apart. Genzel said the observations delivered the best empirical evidence that supermassive black holes do really exist. The mass at the center, he said, must be a black hole, beyond any reasonable doubt. For that work, Genzel and Gies shared the 2020 Nobel Prize in Physics. The data was so precise, so unambiguous, that it closed the door on alternative explanations. Sagittarius A* is a black hole, not a candidate, not a maybe. A confirmed supermassive black hole sitting at the center of our galaxy. This method, tracking the orbits of stars around an invisible mass, is one of the cleanest ways to detect a black hole. You don't need to see the black hole itself, you just need to see what it's doing to the things around it. Gravity doesn't hide, it pulls. And if something is pulling hard enough to make stars orbit at thousands of kilometers per second, you can measure that pull and work backward to figure out what's causing it. The technique works for Sagittarius A*. It works for other galaxies where we can resolve individual stars near the core. It's indirect, yes, but it's definitive. Not all black holes are surrounded by conveniently orbiting stars. Most aren't. Stellar mass black holes drifting alone through the galaxy don't have anything nearby to pull on. They're invisible, and they stay invisible unless something wanders close enough to interact. That's where the second method comes in, X-rays. When a black hole is part of a binary system orbiting a normal star, things get interesting. The black hole's gravity pulls gas off the surface of its companion. That gas doesn't fall straight into the black hole. It spirals, it forms an accretion disk. And as the gas spirals inward, friction heats it. The inner parts of the disk, the regions closest to the event horizon, get hot enough that the gas starts glowing. Not in visible light, in X-rays. Millions of degrees. Hot enough that atoms are stripped of their electrons, and the plasma emits high-energy radiation that punches through the dust and gas of the galaxy and reaches our telescopes. This is how we've detected most of the stellar mass black holes we know about, by their X-ray signatures. Astronomers call these systems X-ray binaries. A normal star orbiting an invisible companion, with a stream of gas flowing from the star toward the companion and glowing in X-rays as it spirals inward. If you measure the mass of the companion using the same orbital mechanics that worked for S2, and if that mass is above about 3 solar masses, the limit for neutron stars, then it's a black hole. No other object can be that massive and that compact without collapsing into a black hole. The first X-ray binary confirmed to contain a black hole was Cygnus X1, discovered in the 1960s, a bright blue supergiant star orbiting something invisible every 5.5 days. The invisible companion weighs about 15 times the mass of our Sun, too heavy to be a neutron star. The system emits powerful X-rays from an accretion disk swirling around the black hole, fed by gas pulled off the supergiant. Cygnus X1 is about 6,000 light-years away, close enough that we can study it in detail, far enough that it poses no danger to us. The black hole is just sitting there, quietly eating its companion star one gas cloud at a time, glowing in X-rays, announcing its presence to anyone with an X-ray telescope pointed in the right direction. X-ray binaries are loud. Compared to isolated black holes, which are completely silent, X-ray binaries are cosmic beacons. The X-ray emission is bright enough to detect across thousands of light-years. And because the emission comes from the accretion disk, not the black hole itself, we're not violating any rules. The gas hasn't crossed the event horizon yet. It's still outside, still visible, still radiating. Once it crosses, the light stops. But before it crosses, the gas glows. And that glow is how we find the black hole. Then there's gravitational lensing. This one is subtle, elegant, and it works even when the black hole isn't feeding, isn't part of a binary, isn't doing anything except sitting there bending space. General relativity says mass curves spacetime. Light follows the curves. If a massive object sits between us and a distant background star, the light from that star has to pass through the curved space around the massive object to reach us. The light bends, the path curves. And from our perspective, the background star appears to shift position slightly, or brighten, or in some cases split into multiple images. This is gravitational lensing. The foreground mass is acting like a lens, bending the light from objects behind it. Black holes are extremely good at this. Even a stellar mass black hole drifting alone through the galaxy will bend the light of any star it passes in front of. The effect is temporary. The black hole moves, the alignment changes, the lensing fades. But during the brief window when the black hole is almost perfectly aligned with the background star, the star's light brightens, sometimes by a noticeable amount. Astronomers can detect that brightening, measure the duration and the light curve, and use the data to calculate the mass of the lensing object. If the mass is high enough and the object is compact enough, it's a black hole. This technique is called gravitational microlensing, and it's one of the few ways to detect isolated black holes that aren't interacting with anything. You don't need an accretion disk, you don't need a companion star. You just need a black hole drifting through the line of sight between us and a distant star. The alignment has to be precise. The effect is rare, but it happens, and every time it does, we get a measurement, a mass, a confirmation that yes, there's a black hole out there, invisible, silent, detectable only by the way it bends the light of something behind it. In 2022, astronomers used microlensing to confirm a stellar mass black hole about 5,000 light-years away. The black hole passed in front of a background star, and for a few months, the star's light brightened as the black hole's gravity focused the light toward us. The lensing event lasted long enough to measure the black hole's mass, about 7 solar masses, compact, isolated, drifting alone through the galaxy, no companion, no accretion disk, no X-rays. Just a dark, invisible knot in space-time, bending the light of a star it happened to pass in front of. This is probably how most stellar mass black holes exist, alone, quiet, invisible, detectable only when chance aligns them with something brighter behind them. Now we get to the big one: gravitational waves. In 1915, the same year Albert Einstein published General Relativity, he worked out another prediction. If space-time is a fabric that can be curved by mass, then it should also be able to ripple, like dropping a stone into a pond. Accelerating masses, especially very massive objects moving very fast, should produce ripples in space-time that propagate outward at the speed of light. Einstein called them gravitational waves. He also thought they'd be too weak to ever detect. The effects are tiny. Space-time is stiff. It takes extraordinary events to make ripples large enough to measure. Einstein predicted gravitational waves would exist, and then he predicted we'd never see them. He was half right. Gravitational waves exist, and for a century they were undetectable. Then, on September 14, 2015, two detectors in the United States, part of a project called LIGO, the Laser Interferometer Gravitational Wave Observatory, recorded a signal, a ripple in space-time passing through Earth. The signal lasted a fraction of a second. The amplitude was absurdly small. The detectors measured a change in distance smaller than 1,000th the width of a proton. But the signal was there, clear, unmistakable. And when physicists analyzed the waveform, they knew exactly what had caused it. Two black holes, each about 30 times the mass of our Sun, had collided and merged. The collision happened more than 1 billion light-years away. The black holes spiraled toward each other, orbiting faster and faster, emitting gravitational waves that carried energy away from the system. As they lost energy, they fell closer. The orbit tightened, the waves grew stronger. And then, in the final fraction of a second, the two black holes merged into one. The merger released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that same moment. For a fraction of a second, that collision was the brightest thing in the universe, not in light, in gravity. The waves traveled outward at the speed of light. For 1 billion years, they crossed the universe, stretching and compressing space as they passed, carrying the signature of the collision encoded in the waveform. And on September 14, 2015, those waves reached Earth. They passed through the planet, through the LIGO detectors, stretching and compressing the arms of the interferometers by a distance smaller than the nucleus of an atom. The detectors caught it, the signal was analyzed, and for the first time in history, humanity detected gravitational waves, and in doing so, confirmed the existence of black holes in a way that didn't rely on light, on orbits, on accretion disks, or on any indirect inference. The black holes announced themselves directly through gravity. Since that first detection, LIGO and its partner observatories have detected dozens of black hole mergers. Some involve black holes heavier than we thought could form from collapsing stars. Some involve black holes spinning so fast they're near the theoretical limit. And one detection, announced in 2017, caught the merger of two neutron stars. That event was detected in gravitational waves and also observed in light. Telescopes across the planet watched the explosion, the afterglow, the radioactive decay. It was the first multi-messenger observation of a cosmic event. Gravity and light telling the same story from two different angles. Gravitational wave astronomy is new. LIGO's first detection was less than a decade ago, but it's already changed the game. For the first time, we're detecting black holes directly, not by watching stars orbit them, not by catching X-rays from their accretion disks, by feeling the ripples in space-time they produce when they move, when they merge, when they spiral. Gravitational waves don't care about dust. They don't get absorbed by gas or scattered by magnetic fields. They pass through everything, which means we can detect black hole mergers anywhere in the universe, as long as the signal is strong enough to reach us. And now we come to the image, the picture, the thing that put black holes on the front page of every newspaper in the world. In April 2019, the Event Horizon Telescope collaboration released the first image of a black hole, not Sagittarius A star. That image came later. The first target was the supermassive black hole at the center of a galaxy called Messier 87, a giant elliptical galaxy sitting 55 million light-years away. The black hole weighs about 6.5 billion solar masses, enormous. And because it's so massive, the event horizon is large enough that even from 55 million light-years away, it spans a measurable angle on the sky. The Event Horizon Telescope is not a single telescope, it's a network. 8 radio observatories scattered across the planet, from Chile to Hawaii to Antarctica, all pointed at the same target at the same time. By combining the data from all 8 sites, the collaboration effectively built a telescope the size of the Earth. The resolving power of a telescope depends on its diameter. Bigger telescope, sharper image. An Earth-sized telescope can resolve details smaller than the event horizon of a supermassive black hole millions of light-years away. That's exactly what they did. What they photographed was not the black hole itself. You can't photograph a black hole. What they captured was the glowing ring of gas orbiting just outside the event horizon, the accretion disk. Superheated plasma spiraling inward at close to the speed of light, emitting radio waves, backlit by its own glow. And in the center of that ring, a shadow, a dark circle. That shadow is the black hole. Light from the accretion disk curves around the black hole due to gravitational lensing. Some of it reaches us, some of it falls in and never escapes. The result is a bright ring with a dark center. The dark center is slightly larger than the actual event horizon because of the lensing, but it marks the boundary, the point of no return, the edge of the black hole. The image is blurry, orange and red and black. It looks almost abstract, but it's real. That ring is real gas, glowing at millions of degrees, orbiting a 6.5 billion solar mass black hole in a galaxy 55 million light-years away. And the shadow in the center is the event horizon, the boundary where space curves so sharply that light can't escape. For the first time in history, we were looking at the edge of a black hole, not inferring it from orbits or X-rays or gravitational waves, seeing it directly. 3 years later, in May 2022, the Event Horizon Telescope released a second image, this time Sagittarius A star, the black hole at the center of our galaxy, 4 million solar masses, 26,000 light-years away. The image looks almost identical to the Messier 87 image, a bright orange ring with a dark center. The ring is the accretion disk. The center is the shadow of the event horizon. Same physics, same geometry, different black hole. Getting the Sagittarius A star image was harder. Messier 87's black hole is so massive that the gas around it orbits over the course of days or weeks. The structure is relatively stable. You can observe it for hours, and the disk doesn't change much. Sagittarius A star is smaller. The gas orbits in minutes. During the hours it took to gather the data, the accretion disk was constantly shifting, flickering, rearranging itself. The image had to be reconstructed using sophisticated algorithms that averaged out the variability. The result is less a photograph and more a statistical reconstruction. But it's real. The ring is there, the shadow is there, and the size of that shadow matches the predictions from general relativity almost exactly. These images are proof, Not indirect proof, not inferred proof. Visual proof that black holes exist, that they have event horizons, that general relativity describes them correctly. The shadow is the fingerprint, the signature, the thing that no other object in the universe can fake. A dark circle surrounded by glowing gas, sitting exactly where the math says the event horizon should be. We've built a toolkit for finding invisible objects, orbital mechanics, X-ray binaries, gravitational lensing, gravitational waves. The Event Horizon Telescope. Each method reveals a different aspect of black holes. Orbits tell us the mass. X-rays tell us they're feeding. Lensing tells us they're bending space. Gravitational waves tell us they're moving, colliding, merging. And the Event Horizon Telescope shows us the shadow, the edge, the boundary between the universe we can see and the region we can't. Each technique is indirect in some way. None of them show the black hole itself, but together they paint a picture so complete, so consistent, that the conclusion is unavoidable. Black holes are real, they're everywhere, and we've learned to see them even though they refuse to emit light. The process has taken a century. From Einstein's equations in 1915 to the first gravitational wave detection in 2015. From the discovery of X-ray binaries in the 1960s to the first Event Horizon Telescope image in 2019. Each step required new instruments, new techniques, new ways of thinking about how to observe something that by definition can't be observed directly. And every step confirmed the same thing. Black holes exist. They bend space, they trap light, they radiate nothing. And yet, through the effects they have on the universe around them, we've mapped them, measured them, photographed their shadows, and confirmed that the predictions Einstein made more than a century ago were correct. Sagittarius A star is invisible, but we've tracked the stars orbiting it. We've measured its mass to within 1% accuracy. We've caught it flaring in X-rays when a clump of gas falls in. We've photographed the glowing ring around its event horizon. We know it's there. We know what it weighs. We know where it sits. We know it's a black hole. And all of that knowledge came from reading the echoes, the fingerprints, the ripples in space-time, and the bending of light and the orbits of stars moving too fast to be explained by anything else. Black holes don't emit light, that's the rule. But there's one exception, one prediction made by Stephen Hawking in the 1970s that says black holes aren't entirely black, that they glow, faintly, slowly, through a quantum process so subtle it's never been observed directly. But if Hawking was right, and most physicists think he was, black holes are not eternal. They evaporate, they radiate, they shrink. And given enough time, every black hole in the universe, including Sagittarius A star, will vanish. Not by falling into something bigger, by slowly leaking energy back into the universe, one photon at a time, until nothing is left. We've talked about detecting black holes, tracking stars, measuring X-rays, catching gravitational waves, photographing the glowing ring around the event horizon. All of it pointed to the same conclusion. Black holes exist. They trap light, they bend space, they swallow matter. And once something crosses the event horizon, it's gone forever. That was the rule. The absolute, unbreakable law written into the geometry of space-time itself. Cross the boundary and there's no coming back. The black hole keeps everything, forever. Except it doesn't. In 1974, a 32-year-old physicist at Cambridge University named Stephen Hawking published a paper that changed everything. The title was dry, technical, the kind of thing that sounds boring until you realize what it's actually saying. The paper showed that black holes are not perfectly black, that they glow. faintly, slowly, through a quantum process that nobody had predicted and that still, 50 years later, has never been directly observed. Hawking showed that black holes can lose mass, that they radiate, that they shrink, and that, given enough time, every black hole in the universe, from the smallest stellar remnant to the largest supermassive monster, will evaporate. Not by falling into something bigger, not by merging, by leaking energy back into the universe, one photon at a time, until nothing is left. This was not a small revision to the theory. This was a bomb. Black holes were supposed to be eternal. Cosmic prisons with no exit, no parole, no appeal. Hawking showed they have a finite lifespan. They're not permanent, they're temporary. And the mechanism that kills them, the radiation that slowly drains their mass, is so subtle, so deeply rooted in the clash between quantum mechanics and general relativity, that it took one of the brightest minds in physics to even notice it was there. Here's the setup. General relativity describes gravity as the curvature of space-time. It works beautifully at large scales: planets, stars, galaxies, black holes. The equations are elegant, precise, and they've been tested over and over again. Every prediction Einstein made has held up. Time dilation, gravitational lensing, gravitational waves, the bending of light around massive objects, all confirmed. General relativity is not speculative. It's one of the most successful theories in the history of science. Quantum mechanics describes the behavior of particles at very small scales: atoms, electrons, photons, quarks. It's also extraordinarily successful. Every piece of modern technology, from computer chips to lasers to MRI machines, relies on quantum mechanics. The theory has been tested in laboratories for a century, and it works. The predictions are accurate to absurd levels of precision. Quantum mechanics is as close to unshakable as a scientific theory gets. The problem is that the two theories don't talk to each other. General relativity assumes space-time is smooth, continuous, predictable. Quantum mechanics says the universe at small scales is probabilistic, fuzzy, fluctuating. And when you try to combine them, when you try to describe what happens in a region where both gravity and quantum effects matter, the math explodes. The equations give nonsensical answers, infinities, contradictions, predictions that can't be tested because the numbers stop making sense. There are very few places in the universe where both theories matter at the same time. Most of the time, you can use one or the other. Describing the orbit of a planet, general relativity. Describing the behavior of an electron, quantum mechanics. But near the event horizon of a black hole, you need both. Gravity is extreme. Space-time is curved to the breaking point. And at the same time, quantum effects, the probabilistic nature of particles and fields, don't just disappear because gravity is strong. They're still there, still operating, still doing what quantum mechanics says they should do. This is where the two theories collide. And this is where Hawking found something nobody expected. Quantum mechanics says that empty space is not empty. Even in a perfect vacuum, with no particles, no matter, no energy, the quantum fields that permeate the universe are fluctuating, constantly. These fluctuations are called virtual particles, and they appear in pairs, a particle and an antiparticle. They pop into existence out of nothing, exist for a tiny fraction of a second, and then annihilate each other, vanishing back into the vacuum. This happens everywhere, all the time. In the room you're sitting in right now, virtual particles are appearing and disappearing faster than anything you could ever measure. They're a prediction of quantum field theory, and the effects they produce have been confirmed in experiments. Virtual particles are real in the sense that they have measurable consequences, they're just not permanent. Now take that process and move it to the edge of a black hole, right at the event horizon. Virtual particle pairs are still forming. A particle and an antiparticle pop into existence, just like they do everywhere else in the universe. But here, near the event horizon, something different can happen. One member of the pair, let's say the antiparticle, can fall across the horizon before the pair has a chance to annihilate. It's gone, trapped inside the black hole. The other member, the particle, is left outside, and because its partner disappeared, it doesn't have anything to annihilate with. It escapes. It becomes real. A permanent particle carrying energy away from the black hole. Where did the energy come from? The black hole. The particle that escaped is positive energy. The antiparticle that fell in is negative energy, at least from the perspective of the black hole's mass. The black hole loses mass, a tiny amount, an absurdly tiny amount, but it's real. The black hole has radiated a particle, and this process, this quantum separation of particle pairs at the event horizon, happens continuously, slowly, one particle at a time, over enormous spans of time, but it happens. This is Hawking radiation. The black hole is glowing, not brightly, not in any way you could see with a telescope. The radiation is thermal, meaning it's essentially random heat, and the temperature of a black hole is inversely proportional to its mass. The bigger the black hole, the colder it is. A black hole with the mass of our Sun would have a temperature of about 60 nanokelvins. That's 60 billionths of a degree above absolute zero. Colder than the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. A solar mass black hole is colder than empty space. It's not losing mass. It's gaining mass, because it's absorbing more energy from the cosmic microwave background than it's radiating. But smaller black holes are hotter, much hotter. A black hole with the mass of a mountain, about 1 billion tons, would have a temperature of about 100 billion degrees Kelvin. Hot enough to radiate gamma rays. Hot enough to glow brightly, not in any visible way, but in terms of the energy it's pouring back into the universe. And a black hole that small would evaporate quickly, not in a human lifetime, but in cosmological terms, fast. It would radiate away its entire mass in something like 10 billion years, roughly the current age of the universe. Supermassive black holes, the kind sitting at the centers of galaxies, are cold, incredibly cold. Sagittarius A star, weighing 4 million solar masses, has a Hawking temperature of about 15 trillionths of a degree above absolute zero. It's not evaporating, not in any measurable sense. Not now. The cosmic microwave background is too warm. The black hole is absorbing far more energy from the universe around it than it's radiating. But the universe is expanding. The cosmic microwave background is cooling. In a few trillion years, the background radiation will have cooled below the temperature of even the largest black holes. At that point, every black hole in the universe will start losing mass, slowly, radiating, shrinking. The lifetime of a black hole scales roughly as the cube of its mass. Double the mass, and the evaporation time goes up by a factor of 8. A black hole with one solar mass would take more than 10 to the 67th power years to evaporate. That's a 1 followed by 67 zeros. For reference, the current age of the universe is about 10 to the 10th power years, a 1 followed by 10 zeros. The lifetime of a solar mass black hole is longer than the age of the universe by a factor of 10 to the 57th. That's not a number you can visualize. It's older than old. It's so far into the future that the concept of time starts to lose meaning. Supermassive black holes take even longer. The black hole at the center of the Milky Way, 4 million solar masses, would take something like 10 to the 100th power years to evaporate. maybe longer, depending on how much mass it accretes over the next few trillion years. The biggest black holes in the universe, the ones weighing tens of billions of solar masses, might last 10 to the 106th power years. These are timescales that dwarf the lifetime of stars, of galaxies, of everything we think of as permanent. But they're finite. Hawking showed that no black hole lasts forever. They all die, eventually. When Hawking first presented this result, the reaction was mixed. Some physicists thought it was brilliant, others thought it was wrong. The idea that black holes could radiate seemed to violate everything general relativity said about event horizons. The event horizon is a boundary where escape velocity exceeds the speed of light. Nothing can cross it outward. Not matter, not energy, not information. That's the rule. And here was Hawking saying that actually, yes, energy can escape, not by crossing the horizon in the classical sense, by quantum tunneling, by a process that doesn't exist in general relativity, but is perfectly allowed in quantum mechanics. The debate went on for years. Hawking refined the argument. Other physicists checked the math, and eventually the consensus settled. Hawking was right. Black holes radiate. The process is real. It's a genuine prediction of quantum field theory in curved space-time. Nobody has ever detected Hawking radiation directly. The effect is far too weak. Even the hottest black holes we know about are too cold to produce detectable radiation, but the theoretical foundation is solid. Most physicists accept that Hawking radiation exists, that black holes evaporate, that they're not eternal. There's a wrinkle, a big one. Hawking radiation is thermal, it's random. It carries no information about what fell into the black hole. If you throw a book into a black hole, the information in that book, the words on the pages, the arrangement of atoms, everything that made it a book, is gone. The black hole radiates heat, random photons, particles with no memory of what the black hole swallowed. And when the black hole finally evaporates, when the last particle radiates away and the black hole disappears, the information is lost forever. This is the information paradox. Quantum mechanics says information can't be destroyed. It can be scrambled, hidden, encoded in ways that are hard to read, but it has to be preserved. That's one of the foundational principles of quantum theory. If you know the state of a system at one time, you can in principle calculate its state at any other time. The evolution of a quantum system is reversible. Information is conserved. But if black holes destroy information, quantum mechanics is wrong. If a book falls into a black hole and the black hole evaporates into random thermal radiation, the information in that book is gone. There's no way to reconstruct it. The quantum state of the universe has lost information, and that's not allowed. At least, it's not supposed to be allowed. Hawking, in 1981, argued that information falling into a black hole is irretrievably lost, that the paradox is real. That quantum mechanics, at least in this extreme case, breaks down. Most physicists disagreed, not because they had a solution, because they couldn't accept that information could be destroyed. It would break too many other things. The foundations of quantum theory would crumble. The universe would stop making sense in ways that go far beyond black holes. The debate has been running for more than 40 years. Nobody has solved it. The leading idea is that information is somehow encoded on the event horizon itself, smeared across the surface in a way that allows it to eventually escape as the black hole evaporates. This is connected to an idea called the holographic principle, which says that all the information inside a volume of space can be encoded on the boundary of that volume. If that's true, the event horizon isn't just a passive boundary, it's a storage system. a two-dimensional surface that holds all the information about everything that ever fell into the black hole. And as the black hole evaporates, that information leaks back out in the Hawking radiation, scrambled beyond recognition, but technically still there. This is speculative. It's cutting-edge theoretical physics, and the details are still being worked out. But the idea has gained traction because it's one of the few proposals that preserves both quantum mechanics and general relativity. The information isn't destroyed, it's hidden. And when the black hole finally dies, the information comes back. Maybe not in a form you can read, maybe not in a way that lets you reconstruct the book you threw in, but the information is there, encoded in the correlations between particles, in the entanglement of the radiation, in structures so subtle that we don't yet have the math to fully describe them. Hawking himself changed his mind. In 2004, he gave a talk at a conference in Dublin where he conceded that information is probably not destroyed. That black holes must return the information somehow, even if the mechanism is unclear. He'd spent decades arguing the opposite, but the weight of evidence, the arguments from other physicists, the implications for quantum mechanics eventually convinced him. Information, he said, finds a way out. It has to. Whether he was right about that is still an open question. The information paradox is one of the deepest unsolved problems in theoretical physics. It sits right at the intersection of quantum mechanics and gravity, the two pillars of modern physics that refuse to merge into a single coherent framework. Solving the paradox will probably require a theory of quantum gravity, a unified description that combines both theories without the infinities and contradictions that show up when you try to do it now. String theory is one candidate. Loop quantum gravity is another. Neither is complete. Neither has made predictions that can be tested with current technology. The paradox remains. But here's what we know for certain. Black holes are not eternal. Hawking proved that. The radiation is real, even if we've never detected it. The process is slow, absurdly slow, for any black hole massive enough to have formed naturally. But it's there, and given enough time, every black hole in the universe will evaporate. The small ones first. Stellar mass black holes, then the intermediate mass ones. Then, trillions upon trillions of years from now, the supermassive monsters sitting at the centers of galaxies. Sagittarius A star will evaporate. So will the black hole in Messier 87. So will every black hole we've ever detected, every one we haven't, every one that will form in the future. They all die. The final stage of evaporation is violent. As a black hole loses mass, its temperature increases. The radiation gets stronger. The evaporation accelerates. A black hole that's been slowly leaking photons for 10 to the 100th power years will, in its final moments, radiate away the last of its mass in a sudden burst of energy. One estimate compares the terminal explosion to 1,000,000 1-megaton hydrogen bombs going off simultaneously. A flash of gamma rays and particles, the black hole's dying scream, and then nothing. No event horizon, no singularity, no gravitational pull, just empty space and a fading cloud of radiation. That's the fate of every black hole, not swallowed by something bigger, not drifting forever through an expanding universe. Evaporation, slow death by quantum leakage. The universe's most absolute boundaries, the one-way membranes that nothing can cross, are not permanent. They're temporary structures, long-lived, yes, longer than anything else we know about, but temporary. This changes the story. Before Hawking, black holes were cosmic graves, final resting places where matter and energy went to be locked away forever. After Hawking, they're more like slow-release reservoirs. They hold matter for a time, an incomprehensibly long time, but eventually they give it back. The information, the energy, the mass, all of it returns to the universe, scrambled, thermalized, spread across space in the form of random particles and radiation, but returned. The implications are staggering. If black holes evaporate, the universe has a clock, a very, very slow clock, but a clock nonetheless. In the far future, long after the last stars have burned out, long after galaxies have drifted apart and the universe has gone cold and dark, black holes will be the last objects radiating energy. They'll sit there, glowing faintly, losing mass one photon at a time. And eventually, even they will be gone. The universe will be empty. No stars, no galaxies, no black holes. Just a thin gas of particles and radiation, spreading outward, cooling, fading into nothing. This is the heat death of the universe, the final state predicted by thermodynamics. A state of maximum entropy where nothing interesting can happen anymore because there's no energy left to do anything with. Black hole evaporation is one of the final chapters in that story. After the stars die, black holes evaporate. After the black holes evaporate, there's nothing left but radiation and the slow, inexorable expansion of space. We are nowhere near that future. The universe is young, stars are still forming, galaxies are still colliding, black holes are growing, not shrinking. Sagittarius A star is accreting gas, not radiating. The cosmic microwave background is too warm. The universe is too full. Hawking radiation is a theoretical prediction, not an observable phenomenon. Not yet, not for trillions of years, but it's real. The math is solid. The prediction is unambiguous. Black holes evaporate, and when they do, they leave nothing behind. In 2021, a team of physicists analyzed data from gravitational wave detectors and found the first direct observational confirmation of one of Hawking's other predictions. In 1971, 3 years before his radiation paper, Hawking derived what's now called the black hole area theorem. The idea is that the surface area of a black hole's event horizon should never decrease. Black holes can merge, and when they do, the area of the combined event horizon is always larger than the sum of the two original horizons. Black holes can accrete matter, and the area increases, but the area should never shrink. It's analogous to the second law of thermodynamics, which says that entropy never decreases. Hawking's area theorem says the same thing about black hole horizons. The 2021 study looked at gravitational wave signals from a black hole merger detected by LIGO. They measured the masses and spins of the two black holes before the merger and compared them to the mass and spin of the final black hole after the merger. By calculating the surface area of the event horizons, they confirmed that the area of the final black hole was larger than the combined areas of the two original black holes. The confidence level was 95%. It was the first time anyone had tested the area theorem with real data. And it held. Hawking was right, again. The area theorem is connected to Hawking radiation in subtle ways. Both ideas come from treating black holes as thermodynamic objects, objects with temperature, entropy, and energy. Before Hawking, black holes were described purely by general relativity. After Hawking, they became thermodynamic systems. They have temperature, they radiate. They obey laws that look like the laws of thermodynamics. The area of the event horizon is proportional to the black hole's entropy. And just like entropy in the universe as a whole, the entropy of a black hole increases over time. Unless the black hole is evaporating, then the entropy decreases, and that's where the subtlety comes in. The black hole's entropy decreases, but the entropy of the universe as a whole still increases because the radiation carries entropy away. The second law of thermodynamics is safe. The universe still marches toward heat death. Hawking radiation doesn't violate the second law. It obeys it, in a deeper, stranger way than anyone expected. 50 years after Hawking's paper, black holes are no longer the unchanging, eternal objects they were once thought to be. They're dynamic. They grow, they merge, they radiate, they evaporate. They interact with the universe around them in ways that general relativity alone can't describe. Hawking showed that black holes sit at the boundary between two theories, quantum mechanics and general relativity, and that understanding them fully requires both. We don't have a complete theory yet. Quantum gravity is still out of reach, but Hawking gave us a glimpse of what that theory will have to explain. Black holes glow, they die, and when they die, they take with them one of the deepest mysteries in physics. What happens to information when it falls into a region from which nothing can escape? The answer is still unclear, but Hawking showed us where to look. Black holes are not eternal. That's the revelation. They're temporary structures in a universe that's moving, slowly but inevitably, toward a state of maximum entropy. They last longer than anything else, longer than stars, galaxies, planets, civilizations, but they don't last forever. And in the unimaginably distant future, when the last black hole evaporates, the universe will have passed through its final major phase transition. The era of structure, of complexity, of interesting things happening will be over. What's left will be a thin, cold, expanding soup of particles and radiation, drifting apart, cooling toward absolute zero, fading into silence. That's the end point. That's where the universe is heading. And black hole evaporation is one of the last acts in that long, slow decline. We're living in the early chapters. The universe is still young, still full of energy, still building galaxies and lighting stars. But the ending is written. And black holes, strange as it sounds, are part of what tells us how the story ends. We've talked about what happens when black holes die, how Hawking radiation, that slow quantum leakage at the event horizon, guarantees that no black hole lasts forever, how even Sagittarius A star, sitting at the center of our galaxy, will eventually evaporate into a fading cloud of particles trillions upon trillions of years from now. The universe has a clock, a very slow clock, but the ending is written. Black holes are temporary. Strange as that sounds, they don't last. But that's the far future, the heat-death endgame, the final chapter in a story that won't finish for timescales so long the numbers stop meaning anything. Right now, today, the universe is still building black holes, still growing them, still smashing them together in collisions violent enough to ripple space-time itself. And the more we look, the stranger the population gets, because black holes don't come in just two sizes: stellar mass remnants weighing a few dozen suns, and supermassive monsters weighing millions or billions. There's a whole range in between. A murky middle ground where the observations are thin, the formation mechanisms are unclear, and the objects we've found don't fit neatly into any category. This is the frontier, the edge of what we know, and it's where some of the biggest surprises are hiding. Let's start with the gap, the missing link, the black holes that should exist, but that we've barely found. Stellar mass black holes form from collapsing stars. We've covered that. Massive star dies, core collapses, supernova, black hole. The remnant weighs somewhere between 3 and maybe 100 solar masses, depending on how massive the star was and how much mass got blown away in the explosion. These objects are common. Our galaxy probably contains tens of millions of them. Most are invisible, drifting alone through the dark. Some are in binary systems, feeding on companion stars, glowing in X-rays. We've detected hundreds. We understand how they form. The physics is solid. Supermassive black holes sit at the centers of galaxies. Sagittarius A star weighs 4 million solar masses. The black hole at the center of Messier 87 weighs 6.5 billion. These things are enormous. And they didn't form from single stars. They were built over billions of years through accretion, mergers, and possibly direct collapse of massive gas clouds in the early universe. We've found more than 150 of them with direct mass measurements, and indirect observations suggest nearly every large galaxy has one. The correlation between black hole mass and galaxy mass is tight, consistent, and spans the entire observable universe. Supermassive black holes are not rare, they're standard equipment. But between 100 solar masses and 100,000 solar masses, there's almost nothing. That's the gap, the intermediate mass range. And it's not that we haven't looked, we've looked. Astronomers have been searching for intermediate mass black holes for decades. The problem is we keep not finding them, or more accurately, we keep finding hints, candidates, maybes, objects that might be intermediate mass black holes or might be something else entirely. The data is messy, the detections are ambiguous, and the lack of clear confirmations is one of the biggest unsolved puzzles in black hole astronomy. Why does the gap matter? Because if supermassive black holes grew from stellar mass seeds, there should be a population of intermediate mass black holes scattered through the universe. Transitional objects, black holes that started small and are still growing, seeds that haven't reached supermassive status yet. The absence of a clear population in that range suggests something about the growth process we don't understand. Maybe intermediate mass black holes are rare because they grow quickly. Once a black hole hits a few hundred solar masses, maybe it accelerates, feeding faster, merging more often, jumping to supermassive in a cosmologically short time. Maybe the intermediate phase is so brief that most black holes skip through it before we get a chance to observe them. Or maybe they're out there and we're just not seeing them. Intermediate mass black holes wouldn't sit at the centers of large galaxies. Those slots are taken. They'd be in smaller systems, dwarf galaxies, globular clusters, dense stellar environments where a black hole could grow by consuming nearby stars and merging with other black holes. These environments are harder to study, the distances are larger, the signals are weaker, and if the black hole isn't actively feeding, if it's sitting quietly without an accretion disk, it's nearly impossible to detect. One of the best candidates we've found is in a globular cluster, a dense ball of old stars orbiting the outskirts of our galaxy. In 2021, astronomers used the Hubble Space Telescope to study the motion of stars in a cluster called NGC 6904. The stars in the core were moving faster than expected. Something massive was pulling on them. By measuring the velocities and running the orbital dynamics backward, the team calculated that the cluster contains a black hole weighing about 2,400 solar masses, right in the intermediate range, not stellar mass, not supermassive, something in between. The detection isn't perfect. The black hole is invisible. We're inferring its presence from the motion of stars, the same technique that confirmed Sagittarius A star. But the environment is messier. Globular clusters are crowded, tens of thousands of stars packed into a region only a few light years across. Measuring individual stellar velocities in that chaos is hard. The uncertainties are larger. And there's always the possibility that what we're seeing isn't a single intermediate mass black hole, but a cluster of smaller objects, stellar mass black holes or neutron stars, whose combined gravity mimics the signature of something bigger. The data points to an intermediate mass black hole, but it's not definitive. Other candidates come from X-rays, bright, persistent X-ray sources in distant galaxies that are too luminous to be powered by stellar mass black holes, but too faint to be the supermassive monsters at galactic cores. Astronomers call these objects ultra-luminous X-ray sources, ULXs. The name is literal. They're brighter than any stellar mass black hole should be, shining with the light of millions of suns, all concentrated in a region smaller than a solar system. For years, ULXs were assumed to be intermediate mass black holes. The logic was simple. The X-ray emission comes from an accretion disk. The brightness depends on how much matter is falling in and how massive the black hole is. If the source is too bright for a stellar mass black hole, it must be bigger. Intermediate mass. Case closed. Except the data didn't cooperate. When astronomers looked closer, when they measured the X-ray spectra and the timing of the emission, some ULXs started looking less like intermediate mass black holes and more like stellar mass black holes feeding unusually fast. Faster than the Eddington limit, the theoretical speed limit on how quickly a black hole can accrete matter. If a black hole tries to eat faster than the Eddington limit allows, the radiation pressure from the infalling gas should blow away the surrounding material, shutting off the food supply. That's the rule, but ULXs seem to be breaking it. One explanation is super-Eddington accretion. If the geometry of the accretion disk is just right, if the magnetic fields are configured in a specific way, maybe a stellar mass black hole can feed faster than the standard models predict without blowing itself out. The disk becomes geometrically thick, funneling matter inward along the poles while radiation escapes perpendicular to the disk. The result is an object that looks overluminous from certain angles, but is still just a stellar mass black hole working overtime. This model fits some ULXs, not all of them, but enough that the intermediate mass interpretation is no longer the default. Other ULXs might be genuine intermediate mass black holes. The jury is still out. The problem is that, from a distance, it's hard to tell the difference. You can measure the X-ray brightness, you can analyze the spectrum, but without a direct mass measurement, without tracking stars or detecting orbital motion, you're left guessing, and most ULXs are too far away for those techniques to work. We see the glow, we measure the energy, we build models, but the models have free parameters, assumptions about the accretion rate and the disk geometry and the magnetic field strength. Tweak the assumptions and you can fit the data with either a stellar mass black hole feeding fast or an intermediate mass black hole feeding slowly. Both work. Neither is ruled out. This ambiguity is frustrating. Intermediate mass black holes should exist. The gap between stellar mass and supermassive has to be filled somehow, but confirming them has turned out to be extraordinarily difficult. Every candidate comes with caveats. Every detection has alternative explanations, and the lack of a clear, unambiguous population of intermediate mass black holes is one of the biggest holes in our understanding of how supermassive black holes form and grow. Then there's the other extreme. Not the largest black holes, the smallest. Objects that might have formed not from collapsing stars, but from the chaotic conditions of the early universe itself. Primordial black holes, hypothetical, unconfirmed. And if they exist, possibly hiding in plain sight as part of the dark matter that holds galaxies together. Here's the idea. In the first fractions of a second after the Big Bang, the universe was not smooth, it was lumpy. Density fluctuations, regions where matter was slightly denser than average, separated by regions where it was slightly less dense. Most of these fluctuations were small, and they grew slowly over millions of years, eventually collapsing into the first stars and galaxies. But if some of the fluctuations were large enough, dense enough, they could have collapsed immediately, not into stars, into black holes, primordial black holes, formed in the first second of the universe's existence, before the first atoms, before the first light, before anything resembling structure had a chance to assemble. Primordial black holes wouldn't follow the mass limits of stellar mass black holes. A stellar mass black hole needs a massive star to form, and massive stars have a minimum size. Below about 3 solar masses, the core doesn't have enough gravity to collapse all the way to a black hole. You get a neutron star instead, but primordial black holes could form at any mass. In principle, they could weigh as little as the Planck mass, about 22 micrograms, or as much as thousands of solar masses. The range is wide open because the formation mechanism doesn't depend on stellar evolution. It depends on the density fluctuations in the early universe, and those fluctuations could have had any amplitude. Nobody knows if primordial black holes are real. They're a prediction, not an observation. The conditions required are extreme, and it's not clear whether the early universe actually had density fluctuations large enough to trigger immediate collapse. Some models of inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang, predict large fluctuations. Others don't. The physics is speculative. But the idea is tantalizing because primordial black holes, if they exist, could solve more than one mystery. Dark matter is one of the biggest unsolved problems in cosmology. Galaxies rotate too fast. Clusters hold together too tightly. The gravity from visible matter, stars and gas and dust, isn't enough to explain the motions we observe. Something else is out there, something massive. Something that doesn't emit light, doesn't absorb light, doesn't interact with normal matter except through gravity. We call it dark matter, and it makes up about 85% of the matter in the universe. We know it's there because we see its gravitational effects. But we've never detected a dark matter particle directly, not in a laboratory, not in a detector, not anywhere. Primordial black holes could be the dark matter, or at least part of it. Black holes don't emit light. They interact only through gravity. And if the early universe produced a population of primordial black holes weighing, say, 10 to 100 solar masses each, they'd be nearly impossible to detect individually, but their collective gravity would hold galaxies together exactly the way dark matter does. The idea has been around since the 1970s, and for a while it was taken seriously. Then observations started closing the window. Gravitational microlensing surveys, the same technique we talked about earlier for detecting isolated black holes, have searched for primordial black holes by watching for the brightening of background stars as a black hole drifts through the line of sight. Those surveys found some events, but not nearly enough to account for all the dark matter. If primordial black holes made up the bulk of dark matter, we'd see far more lensing events than we do. The data rules out primordial black holes as the dominant component of dark matter, at least in the mass ranges those surveys can detect. But there's still room. Primordial black holes could exist in smaller numbers. They could be part of the dark matter, not all of it, or they could exist in mass ranges that microlensing surveys can't probe. Very small primordial black holes, weighing less than a solar mass, would be too light to produce detectable lensing. Very large ones, weighing thousands of solar masses, are harder to rule out because they'd be rarer, and the lensing events would be longer, subtler, easier to miss. The window is narrow, but it's not closed. In 2021, some researchers proposed that the black holes detected by LIGO, the Gravitational Wave Observatory, might be primordial. LIGO has detected dozens of black hole mergers, and some of those black holes are heavier than astronomers expected stellar mass black holes to be. 30 solar masses, 40, in one case more than 60. Stars that massive should be rare, and the black holes they leave behind should be rarer still. But LIGO is finding them regularly. One explanation is that some of these black holes aren't stellar remnants at all. They're primordial, formed in the early universe, drifting through space for billions of years, and now colliding and merging in events violent enough to send gravitational waves rippling across the cosmos. This is speculative. The LIGO black holes could all be stellar remnants. The formation models might just be wrong about how common very massive stars are, or the black holes could be growing by accreting gas after they form, bulking up beyond the masses their progenitor stars would predict. Primordial black holes are one explanation, not the only one. But the fact that it's even on the table shows how much we still don't know about the black hole population. Gravitational wave astronomy has changed the game. LIGO and its partner observatories, Virgo in Europe and Kagra in Japan, have opened an entirely new way to study black holes. Not by watching the light from gas swirling around them, not by tracking the orbits of nearby stars, by feeling the ripples in space-time they produce when they move, when they merge, when they spiral together and collide in events so violent they shake the fabric of the universe itself. The first detection, in September 2015, caught two black holes, each about 30 solar masses, colliding more than 1 billion light-years away. The merger released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that same moment. For a fraction of a second, that collision was the brightest thing in the universe, not in light, in gravity. The waves traveled outward at the speed of light, stretching and compressing space as they passed, and when they reached Earth, they compressed and stretched the arms of the LIGO detectors by a distance smaller than the nucleus of an atom. The detectors caught it, the waveform was analyzed, and for the first time, humanity detected gravitational waves and confirmed the existence of black holes in a way that didn't rely on light, on gas, on orbits, or on any indirect inference. Since then, LIGO has detected dozens of black hole mergers. Some involve black holes heavier than anyone expected. Some involve black holes spinning near the theoretical maximum. And one detection in August 2017 caught the merger of two neutron stars. That event was seen in gravitational waves and also observed in light. Telescopes across the planet watched the explosion, the afterglow, the radioactive decay. It was the first multi-messenger observation of a cosmic event, gravity and light telling the same story from two different angles, confirming that the source was real, that the distance was correct, that the physics matched the predictions. Gravitational wave detectors are getting better. LIGO is being upgraded. A new detector called LISA, the Laser Interferometer Space Antenna, is scheduled to launch in the 2030s. LISA won't sit on the ground like LIGO. It will orbit the Sun, a constellation of 3 spacecraft separated by millions of kilometers, listening for gravitational waves at lower frequencies than LIGO can detect. LIGO is sensitive to stellar mass black hole mergers. LISA will detect supermassive black hole mergers, the kind that happen when two galaxies collide and their central black holes spiral together over millions of years. Those mergers produce gravitational waves at frequencies too low for LIGO to hear, but LISA will catch them. And when it does, we'll have a direct census of supermassive black hole mergers across the history of the universe. Future observatories will push even further. The James Webb Space Telescope is already finding supermassive black holes in the early universe, shining as quasars when the cosmos was less than 1 billion years old. Those black holes are too massive to have formed from stellar seeds in the time available. They require something faster: direct collapse, runaway mergers, primordial seeds. Webb is collecting the data. The next generation of ground-based telescopes, the extremely large telescope in Chile, the 30-meter telescope in Hawaii, will push the observations deeper. Higher resolution, fainter objects, more distant galaxies. Every new instrument opens a new window. Every observation adds a piece to the puzzle. And the puzzle that's emerging is strange. Black holes are everywhere. They come in a wider range of masses than we expected. They grow faster than the models predict. They merge more often than we thought. And the gaps in our understanding, the intermediate mass range, the primordial population, the formation mechanisms in the early universe, those gaps are starting to look less like gaps and more like entire chapters we haven't written yet. We're still in the early stages of black hole astronomy. LIGO has been running for less than a decade. Webb launched in late 2021. The Event Horizon Telescope took its first image in 2019. These are new tools, and they're already rewriting the story. The more we look, the more we find. Stellar mass black holes in binary systems, supermassive black holes at the centers of galaxies, intermediate mass candidates in globular clusters, ULXs that might be black holes feeding faster than they should. Gravitational wave detections of mergers across billions of light years, and hints, just hints, that primordial black holes might be out there, formed in the first moments of the universe, hiding in the dark matter halo, waiting for the right instrument to finally pin them down. The universe is full of black holes, more than we thought, stranger than we expected, and we're only just beginning to map them. Every detection raises new questions. Every measurement refines the models. Every observation pushes the boundaries of what we thought was possible. Intermediate mass black holes should exist. We'll find them. Primordial black holes might exist. We'll test that. Supermassive black holes grew impossibly fast in the early universe. We'll figure out how. The answers are out there, hidden in the data. Encoded in gravitational waves and X-ray flares and the orbits of stars too faint to see with current telescopes, but bright enough that the next generation will catch them. Black holes are not exotic curiosities anymore. They're not rare. They're not poorly understood footnotes in the history of stellar evolution. They're central to how galaxies form, how structure assembles, how the universe grows and evolves and organizes itself across 13.8 billion years of cosmic history. And the more we learn about them, the more we realize how much we still don't know, how many gaps remain, how many questions are still open, how many mysteries are waiting just beyond the edge of what our current instruments can reach. Sagittarius A star sits at the center of our galaxy. 4 million solar masses, a monster by any reasonable standard. But on a cosmic scale, it's small, quiet, typical. There are black holes 1,000 times heavier, black holes feeding so violently they outshine entire galaxies. Black holes colliding and merging in events that ripple space-time across billions of light years. Black holes that might have formed in the first second of the universe's existence and have been drifting through space ever since, invisible, patient, waiting. The universe is stranger than we thought, and black holes are the proof. They sit at the intersection of the largest and smallest scales, the heaviest and the lightest, the brightest and the darkest. They break the rules we thought were absolute. They bend space, they trap light, they radiate, they evaporate, they merge, they grow. And every time we point a new instrument at the sky, we find more of them, in places we didn't expect, doing things we didn't predict. behaving in ways that force us to rewrite the models and rethink the assumptions and admit, once again, that the universe is not required to make sense to us. It just has to be consistent with itself. And black holes, for all their strangeness, are consistent. The math works, the observations fit, the predictions hold. We're living in the golden age of black hole astronomy. The tools are better than they've ever been. The data is richer. The questions are sharper. And the answers, when they come, will reshape not just our understanding of black holes, but our understanding of the universe itself. How it began, how it grew, how it will end. Black holes are not just objects, they're clues, signposts, windows into the deepest, strangest corners of physics. And every discovery, every detection, every new image and waveform and orbital trace brings us one step closer to understanding what they're trying to tell us about gravity, about space-time, about the nature of reality at its most extreme, about what happens when you push the universe to its limits and ask it to show you what's hiding in the dark. We've mapped the population, we've traced the orbits, we've caught the gravitational waves from black holes colliding billions of light-years away, and photographed the glowing ring around the event horizon of the monster sitting at the center of our own galaxy. We've confirmed that black holes exist, that they come in a range of sizes from stellar remnants to supermassive anchors holding galaxies together, that they grow by feeding and merging, that they shape the structures we see across the universe, and that despite being called black, they glow faintly through quantum processes and will eventually, trillions of years from now, evaporate into nothing. That's the inventory, the census, the list of what black holes are and where they sit and what they do. But there's a deeper question sitting underneath all of that. A question that's harder to answer because it's not about the objects themselves, it's about what they mean, what they tell us. What studying them reveals not just about gravity or space-time or the life cycle of stars, but about the nature of reality itself, about the rules the universe runs on, about the limits of what we can know and the gaps in our understanding that we're still trying to close. Black holes are not just astronomical objects, they're laboratories. Natural experiments running at the edge of physics, in conditions so extreme that the theories we use to describe the rest of the universe start to crack. They sit at the boundary between two pillars of modern science, general relativity and quantum mechanics, and they refuse to let us ignore the fact that those two pillars don't fit together. They force questions that wouldn't come up anywhere else. Questions about time, about information, about whether the fabric of space-time is smooth or grainy, about whether the singularities at their centers are real or just mathematical artifacts pointing to a deeper theory we haven't discovered yet. For a century, black holes were theoretical curiosities, solutions to Einstein's equations that seemed too strange to be real. Objects where gravity became so strong that space folded in on itself and time stopped making sense. Most physicists, including Einstein himself, doubted they actually existed. They were mathematical possibilities, not physical objects. Things the equations allowed, but nature would probably find a way to avoid. Then we found them, first indirectly through X-rays and orbital mechanics, then directly through gravitational waves and images of the event horizon itself. And once we confirmed they were real, once we accepted that nature does build these things routinely, the questions shifted. Not whether black holes exist, what they can teach us. The first lesson is about gravity. General relativity, the theory Einstein published in 1915, describes gravity as the curvature of space-time. Mass bends space. Objects follow the curves. The equations are elegant, precise, and they've been tested in every way we know how to test them. time dilation near massive objects, the bending of light around the sun, the precession of Mercury's orbit, gravitational waves from colliding black holes. Every prediction has held up. General relativity works. It describes gravity with a level of accuracy that's almost unsettling, but black holes push the theory to its limits. Near the event horizon, space-time is curved so sharply that light itself can't escape. At the singularity, the curvature becomes infinite, the equations break down. They give answers that don't make physical sense. Infinite density, infinite curvature, divide by zero, and the math explodes. General relativity predicts that singularities exist, but it can't describe what happens at them. The theory reaches a boundary and stops. That boundary is a clue, a sign that something deeper is going on. That general relativity, for all its success, is incomplete. Black holes are the place where that incompleteness shows up most clearly. They're the stress test, the edge case, the regime where gravity is so strong that quantum effects, which general relativity ignores, can't be ignored anymore. And this is where things get messy, because quantum mechanics and general relativity don't speak the same language. They describe the universe in fundamentally different ways. General relativity assumes space-time is smooth, continuous, infinitely divisible. Quantum mechanics says that at small enough scales, everything is discrete, probabilistic, grainy. Particles don't have definite positions until you measure them. Energy comes in chunks. The universe at the quantum level is fundamentally uncertain. For most of physics, you can use one theory or the other, describing the motion of planets, general relativity, describing the behavior of electrons in an atom, quantum mechanics. The two theories don't overlap, so the fact that they don't fit together doesn't cause problems. But near a black hole, you need both. Gravity is extreme, space-time is curved to the breaking point, and at the same time, quantum effects matter. Virtual particles popping in and out of existence near the event horizon, quantum fluctuations in the fabric of space-time itself. You can't ignore either theory, and when you try to use both at once, the math doesn't work. The equations give nonsensical answers, infinities, contradictions, predictions that can't be tested because the numbers stop making sense. This is the problem of quantum gravity, the biggest unsolved problem in theoretical physics. We have two extraordinarily successful theories, general relativity and quantum mechanics, and we don't know how to combine them. Black holes are where that failure shows up most clearly. They're the objects that demand a unified theory, a framework that describes gravity and quantum mechanics together, without the infinities, without the contradictions. String theory is one attempt, loop quantum gravity is another. Neither is complete, neither has made predictions that can be tested with current technology. The problem remains open, but black holes are giving us clues. Hawking radiation, the faint glow at the event horizon, is a genuine quantum effect in a curved space-time. It's a prediction that comes from taking quantum field theory seriously near a black hole. The radiation is real, even if we've never detected it directly. The calculation is solid. It's one of the few places where we've successfully combined quantum mechanics and gravity, at least approximately, and gotten an answer that makes sense. The fact that the answer predicts black holes evaporate, that they're not eternal, is a profound shift. It tells us that black holes are thermodynamic objects, that they have temperature, entropy, and energy. That the event horizon isn't just a geometric boundary, it's a physical surface that encodes information about everything that ever fell in. This is the holographic principle, the idea that all the information inside a volume of space can be encoded on the boundary of that volume. It sounds bizarre. It is bizarre, but it's one of the most important insights to come out of black hole physics in the last 50 years. The surface area of the event horizon is proportional to the black hole's entropy, and entropy measures information. How many ways the microscopic pieces of a system can be arranged while still producing the same macroscopic state. For a normal object, like a box of gas, the entropy depends on the volume. More volume, more space for particles to move around, more entropy. But for a black hole, the entropy depends on the area of the event horizon. Not the volume, the area. That's strange. It suggests that the three-dimensional space inside the event horizon is somehow less fundamental than the two-dimensional surface. That the interior is a kind of holographic projection, encoded on the boundary. This idea has spread far beyond black holes. Some physicists think the entire universe might work this way, that the three-dimensional space we experience is a projection from information encoded on a distant boundary. That reality, at its deepest level, is lower dimensional than it appears. Black holes are where that idea started, and they're still the clearest example we have of a system where the holographic principle seems to hold. The information paradox, the question of what happens to information when it falls into a black hole, is tied directly to this. If the event horizon encodes information, if the holographic principle is correct, then information isn't destroyed when something crosses into a black hole. It's scrambled, encoded on the surface in a way we don't yet fully understand, and eventually released as the black hole evaporates. The details are murky, the mechanism isn't clear, but the broad outline is starting to take shape. Information is preserved, quantum mechanics holds, and black holes, strange as they are, obey the same fundamental rules as everything else in the universe. Testing these ideas requires pushing observations to their limits. The Event Horizon Telescope, the global network that photographed the shadow of the event horizon, is one step. Future upgrades will improve the resolution, allowing us to see finer details in the glowing ring around the black hole. We'll be able to test whether the shadow matches the predictions of general relativity exactly, or whether there are deviations, small differences that might hint at quantum corrections or modifications to Einstein's equations. The measurements are already precise enough to rule out some alternative theories of gravity. As the data improves, the constraints will tighten. If general relativity is wrong, if there are corrections at the scale of the Event Horizon Telescope will see them. Gravitational wave detectors are another tool. LIGO and its partners have detected dozens of black hole mergers, and every detection is a test of general relativity. The waveforms encode information about the masses, spins, and dynamics of the colliding black holes. By comparing the observed waveforms to predictions, physicists can check whether general relativity describes the merger correctly. So far, it does. Every merger matches the predictions to within the measurement uncertainties, but future detectors will be more sensitive. LISA, the space-based gravitational wave observatory planned for the 2030s, will detect supermassive black hole mergers across the history of the universe. Those mergers will produce cleaner, longer-lasting signals than the stellar mass mergers LIGO detects. The data will be richer. The tests will be sharper. And if there are deviations from general relativity, if gravity behaves differently at the scale of supermassive black holes, LISA will catch it. Black holes also offer a window into the early universe. The supermassive black holes we see powering quasars, shining when the cosmos was less than 1 billion years old, shouldn't exist. Not if they grew from stellar mass seeds. There wasn't enough time. The Eddington limit, the speed limit on black hole growth, says it takes hundreds of millions of years to build even a modest supermassive black hole from a stellar remnant. To reach billions of solar masses in less than 1 billion years requires something faster: direct collapse, runaway mergers. primordial seeds formed in the chaotic conditions of the first moments after the Big Bang. We don't know which mechanism is correct. Probably all three played a role. But the existence of supermassive black holes in the early universe tells us something about the conditions back then, about how dense the gas was, how fast galaxies were forming, how often black holes were merging. The James Webb Space Telescope is finding these early quasars, measuring their properties, mapping their host galaxies. Every new detection adds a data point. Every measurement refines the models. And the picture that's emerging is that the early universe was more active, more violent, more efficient at building structure than we expected. Black holes didn't wait politely for galaxies to assemble. They grew fast. They fed voraciously. And they shaped the galaxies around them through feedback, heating gas, driving winds, regulating star formation in ways that determined what those galaxies would look like billions of years later. This connection between black holes and galaxy formation is one of the biggest shifts in modern astrophysics. For decades, black holes were studied as isolated objects, endpoints of stellar evolution, curiosities at the centers of galaxies. But the tight correlation between black hole mass and galaxy mass, the fact that nearly every large galaxy has a supermassive black hole at its center, forced a rethinking. Black holes and galaxies grow together. They're coupled. They influence each other. The black hole heats the gas, limiting star formation. The galaxy feeds the black hole, allowing it to grow. The relationship is symbiotic, regulatory, and it's been running for most of the history of the universe. Understanding that relationship requires understanding feedback, how energy from the black hole, from the accretion disk and the jets and the radiation gets transferred to the surrounding gas, how that energy heats the gas enough to prevent it from collapsing to form stars, how the balance between black hole growth and galaxy growth is maintained. The details are still being worked out. Simulations help. Observations from Webb and future telescopes will help more. But the broad picture is clear. Black holes are not passive. They're active participants in the story of how galaxies form and evolve. They're architects as much as they are destroyers. There's a philosophical dimension to all of this. Black holes challenge our intuitions about what's possible. They trap light. They stop time, at least from an outside perspective. They hide singularities behind event horizons, sealing off regions where the laws of physics, as we currently understand them, break down. They force us to accept that space-time is not a fixed stage, but a dynamic, flexible fabric that can be bent, stretched, torn. That time is not absolute, that the universe, at its most extreme, behaves in ways that seem impossible until you do the math and realize the math is unambiguous. This is what black holes reveal, not just facts about gravity or stellar evolution or galaxy formation, but something deeper, that the universe is stranger than we thought, that our theories, successful as they are incomplete, that there are layers of reality we haven't accessed yet, that the questions we're asking about quantum gravity and information and the nature of space-time at the smallest scales are questions we wouldn't even know to ask if black holes didn't exist. They're also a reminder of scale, of the vastness of the universe and the insignificance of our place in it. Sagittarius, a star, sits at the center of the Milky Way, 4 million times the mass of our Sun, and we orbit it at a distance of 26,000 light-years, moving at 500,000 miles per hour, taking 225 million years to complete one orbit. The black hole has been there for billions of years. It will be there for billions more. It doesn't care about us. It doesn't care about anything. It's a knot in space-time, following the equations, doing what black holes do, bending space, trapping light, growing slowly by accretion and mergers, radiating faintly through quantum processes we barely understand. And when the universe has expanded enough, when the cosmic microwave background has cooled enough, it will start to evaporate, slowly, over timescales, so long the numbers stop meaning anything. But it will evaporate, and when it's gone, nothing will remain, no monument, no record. Just empty space and a fading cloud of radiation. That's the ultimate fate of every black hole. Not permanence, not eternity, evaporation. The universe, it turns out, doesn't keep anything forever. Not stars, not galaxies, not even black holes. Everything is temporary, everything decays, and the heat death that thermodynamics predicts, the final state of maximum entropy where nothing interesting can happen anymore, is the endpoint. Black hole evaporation is one of the last chapters in that story. The last major process that releases energy into a universe that's slowly running out of it. We're nowhere near that endpoint. The universe is young, stars are still forming, galaxies are still colliding, black holes are growing. The cosmic microwave background is still too warm. But the laws that govern the universe don't care about timescales. They run forward regardless, and they point to an ending. A state where all the stars have burned out, all the black holes have evaporated, and all that's left is a thin, cold, expanding soup of particles and radiation, drifting apart, cooling toward absolute zero, fading into silence. Black holes are a window into that future. A glimpse of the machinery that will eventually dismantle everything we see. But they're also a window into the past, into the conditions of the early universe, when galaxies were forming and supermassive black holes were growing impossibly fast, into the moments after the Big Bang, when density fluctuations might have collapsed directly into primordial black holes, into the physics that governs the universe at its most extreme, where gravity and quantum mechanics collide, and the theories we use to describe reality show their limits. Studying black holes is not just about cataloging objects. It's about pushing the boundaries of what we know, about testing the theories that describe space-time, gravity, quantum mechanics, thermodynamics, about searching for the gaps, the places where the math breaks down or gives nonsensical answers, because those gaps are where new physics is hiding. Every observation, every detection, every new image or waveform or orbital trace brings us closer to understanding what black holes are trying to tell us about the universe, about the rules it runs on, about the questions we should be asking, and the theories we need to build to answer them. Sagittarius A star is not unique, it's typical. A standard issue supermassive black hole in a standard issue spiral galaxy. 4 million solar masses, quiet, starving, sitting at the center, bending space, anchoring the Milky Way. But it's also a laboratory, a natural experiment running at the edge of physics, in conditions we could never replicate on Earth. And every time we point an instrument at it, every time we track another star orbiting too close, or catch another flare in X-rays, or refine another image of the glowing ring around its event horizon, we learn something new, not just about Sagittarius A star, about black holes in general, about gravity, about space-time, about the universe itself. This is the final frontier, not a place, a question. What are the limits of physics? Where do our theories break down? What's hiding in the gaps? Black holes are the answer to where those gaps show up most clearly. They're the objects that demand a deeper theory, a framework that unifies quantum mechanics and gravity, a description of reality that works at the singularity, at the event horizon, in the regime where space-time is curved to the breaking point and quantum effects can't be ignored. We don't have that theory yet, but black holes are showing us where to look, what to test, what questions to ask. And when we finally close the gap, when we build a theory of quantum gravity that works, black holes will have been the key, the laboratory, the signpost pointing toward the deeper structure underneath. They've already changed how we think about the universe, about time, about information, about the fabric of space-time itself, and they're not finished. Every new detection, every new observation, every new piece of data refines the picture, tightens the constraints, pushes the theories closer to their breaking points. And when those theories finally break, when we find the deviations from general relativity, or the signatures of quantum corrections, or the evidence of primordial black holes hiding in the dark matter, that's when the real breakthroughs will happen. That's when the next revolution in physics will start. Black holes are not the end of the story, they're the beginning of the next chapter. The chapter where we stop describing the universe with two incompatible theories and start building the framework that unifies them. Where we move beyond general relativity and quantum mechanics and find the deeper structure that contains them both. Where we answer the questions that black holes have been forcing us to ask for a century. What happens at the singularity? Where does information go? Is space-time smooth or grainy? What is the true nature of gravity at the smallest scales? The answers are out there, hidden in the data, encoded in gravitational waves and event horizon shadows and the orbits of stars, too fast to be explained by anything else. And black holes, strange as they are, impossible as they seem, are the key to finding them. You've been living your entire life in orbit around a monster, 4 million times the mass of our Sun, sitting 26,000 light-years away in the direction of Sagittarius, bending space around itself so sharply that light itself can't escape once it crosses the boundary. It's been there longer than our species has existed, longer than our planet has existed. It will be there long after both are gone. And for most of human history, we had no idea. That ignorance wasn't a failure, it was the state of the art. We looked up at the Milky Way and saw beauty, a river of stars cutting across the night. We gave it names, built myths around it, used it to navigate. And the entire time, at the heart of that river, there was a mouth, a knot in space-time that has been quietly anchoring our galaxy, shaping its structure, defining the orbits of hundreds of billions of stars, including ours, and we never suspected. Not because we weren't looking, because we didn't have the tools, now we do. And what we've found is stranger than anyone predicted. Black holes aren't exotic curiosities, they're everywhere. They come in sizes we didn't expect. They grow faster than our models allow. They shape galaxies, they regulate star formation. They merge and send ripples through space-time that we can detect billions of light-years away. They glow faintly through quantum processes and will eventually, trillions of years from now, evaporate into nothing. They sit at the boundary between the two pillars of modern physics, quantum mechanics and general relativity, and they refuse to let us ignore the fact that those pillars don't fit together. Black holes are not the end of the story, they're the beginning of the next one. The chapter where we stop pretending our theories are complete and start building the framework that unifies them, where we move beyond what we know and find the structure underneath. The answers are out there, hidden in the dark,